From the first moment a child drops a stone and watches it fall, there is an unspoken understanding that something invisible moves the world. Long before the equations of Isaac Newton or the curved geometries of Albert Einstein, people sensed a pull between all things, an unseen thread connecting the heavens to the earth. They called it gravity, and it became the first true law of nature. Yet, centuries later, it remains the most mysterious. It shapes the stars, the galaxies, and the very flow of time, but refuses to reveal its deepest workings. It is both the simplest and the strangest of all forces. We live in a universe sculpted by gravity. It gathers dust into planets, planets into systems, and systems into spiraling galaxies that drift through the cosmic sea. It drives the birth and death of stars, ignites fusion, and crushes light itself inside black holes. Every motion, every orbit, every ripple in space-time is its quiet signature. When Einstein reimagined gravity in his general theory of relativity, he replaced Newton's invisible hand with the geometry of space and time themselves. Matter tells space-time how to curve, he said, and space-time tells matter how to move. It was one of the most beautiful sentences ever written in physics. Einstein's equations describe the cosmos not as a stage on which matter plays, but as an actor in the drama itself. Space and time are dynamic, flexible, and alive. They stretch and bend, forming the gravitational fields that guide planets and photons alike. This elegant picture explains almost everything we see at large scales. The motion of planets, the bending of starlight, the expansion of the universe. It has passed every test astronomers could devise, from the delicate precession of Mercury to the detection of gravitational waves rippling across the cosmos. Yet, for all its perfection, general relativity stands apart from the rest of physics. Every other fundamental interaction, electromagnetism, the weak nuclear force, and the strong nuclear force, has been woven into the framework of quantum mechanics. At the smallest scales of existence, particles behave not as solid objects, but as shimmering probabilities, waves of possibility that interfere and entangle. Quantum mechanics has revealed a world where nothing is certain until it is observed, where reality itself is statistical. In this microscopic realm, forces are not continuous fields, but discrete exchanges of energy carried by particles, photons for light, gluons for the strong force, W and Z bosons for the weak. Gravity, however, refuses to join this quantum family. It remains classical, smooth, and continuous, like a fabric without threads. While the other forces operate through quanta, gravity is described as pure curvature. Geometry, not exchange. This divide is the central puzzle of modern physics. The equations that describe atoms and the equations that describe stars cannot coexist in the same space. Try to combine them, and mathematics collapses into infinities. Imagine a star collapsing into a black hole. According to general relativity, the density of matter becomes infinite, the curvature of space-time infinite. The laws of physics break down. According to quantum theory, infinities are forbidden, should quantize, limit, and smooth them out. But when we try to calculate the quantum structure of space-time, gravity explodes into unsolvable contradictions. The smooth surface of Einstein's universe seems to tear when viewed through the quantum lens. Scientists have spent more than a century trying to bridge this divide. They have built particle colliders that smash protons together at nearly the speed of light, probing deeper into the fabric of reality. They have sent telescopes to the edge of the observable universe, watching galaxies recede across billions of years. They have detected gravitational waves from colliding black holes and mapped the cosmic microwave background left from the birth of the universe. Yet the key that unites quantum and gravity remains missing. Why does gravity refuse to fit into the quantum picture? Why does it seem so much weaker than all other forces? If you hold a magnet over a paperclip, the entire mass of the Earth pulling downward is overcome by a small electromagnetic field. The whole planet's gravity cannot defeat the gentle pull of a magnet a few centimeters wide. The weakness of gravity hints at a deep truth. Perhaps it is not truly a force like the others, but something emergent, a manifestation of geometry or information, rather than a fundamental interaction. This possibility disturbs the simplicity of our worldview. We like to think of the universe as made of particles and forces, cleanly categorized and symmetrical, but gravity may be whispering that space, time, and even reality itself are not fundamental things. They might be emergent, rising from something deeper that we have not yet named. Every other force has been captured within the quantum field theory that governs the subatomic world. The electromagnetic field gives rise to photons. The strong field gives rise to gluons. The weak field to W and Z bosons. Each force has its carrier, each field its quanta. Gravity, alone among them, resists this pattern. It has no confirmed messenger particle. It bends space instead of propagating through it. It alters time instead of flowing within it. This contradiction is not just philosophical, it is mathematical, physical, and experimental. General relativity predicts a smooth continuum, while quantum theory insists on discreteness. Somewhere between the smallest possible distance and the largest cosmic scale, the two pictures must merge. But where and how? This is the frontier of modern physics, the place where equations shatter and imagination begins. Somewhere beyond the reach of today's instruments lies the quantum nature of gravity, hidden in the trembling geometry of space-time itself. If every other force is quantum, why should gravity be the exception? That question, simple and relentless, drives the search for the next revolution in physics, the unification of the cosmos and the quantum. The story of gravity is the story of stubborn beauty. It fits everything we can see and touch, yet resists being broken down into the microscopic pieces that make up everything else. When Einstein wrote his equations in 1915, he gave the universe a kind of poetry. Space and time were not empty, they were elastic. The sun did not pull the earth with an invisible string. Instead, the presence of the sun curved the geometry of the region around it, and the earth simply followed the straightest possible path in that curved geometry. To most minds, this sounded like philosophy, yet experiment after experiment proved that it was truth. Light bends as it passes near a star. Clocks run slower in stronger gravitational fields. The very concept of simultaneity fades when we move between speeds and altitudes. Gravity, in Einstein's picture, was not a force acting at a distance, but a manifestation of the shape of reality itself. This smooth geometric world, though, has no place for the jittering chaos of the quantum. The quantum world is not smooth but granular, a restless sea where every particle is both a wave and a point, a presence and a possibility. The energy of a field can only take on certain discrete values. A photon is a packet of electromagnetic vibration. An electron moves not in a definite orbit, but in a cloud of probability. In this strange realm, the observer and the observed are never fully separate. Measuring one property disturbs another. The fabric of existence seems woven from uncertainty. Trying to fit gravity into this quantum sea is like trying to paint a wave on glass. General relativity describes a universe that curves smoothly under the weight of mass and energy. Quantum theory describes one that fluctuates constantly, with energy appearing and disappearing in every instant. When physicists attempt to quantize gravity, to describe it with the same language of fields and particles that works so well elsewhere, the equations produce infinities that cannot be renormalized. The mathematics refuses to settle, yet nature itself must be consistent. Black holes exist, and they compress both quantum fields and curved space-time into the same tiny regions. The early universe, too, was a cauldron where densities and energies reached extremes beyond imagination. In those moments, gravity could not have remained purely classical. It must have behaved quantum mechanically, even if we do not yet know how. The unification of the large and the small is not just an intellectual goal, it is a necessity. Physicists have tried many paths. One idea is that gravity should be described by a particle called the graviton, a quantum of space-time curvature with spin 2 and 0 mass. If such a particle exists, it would mediate gravitational attraction in the same way that photons mediate light. But gravity is extraordinarily weak. Two electrons repel each other through electromagnetism billions upon billions of times more strongly than they attract each other through gravity. Detecting a single graviton would require an experiment so massive that it would collapse into a black hole under its own weight. Because of this, gravity has remained beyond the reach of direct quantum tests. The gravitational waves that LIGO detects come from collisions of black holes or neutron stars, events that release more energy than all the stars in the universe combined for a brief moment. Yet even those signals are classical waves, not individual gravitons. We can see the trembling of space-time, but not its smallest vibrations. Some researchers wonder if we have been asking the wrong question. Perhaps gravity is not a force to be quantized, but an emergent phenomenon, like temperature or pressure. Just as heat arises from the collective motion of countless molecules, gravity might arise from the collective behavior of microscopic degrees of freedom that we have not yet identified. In that case, trying to find the graviton would be like trying to find the atom of heat. The search itself would miss the point. Others pursue the unification more directly. String theory, for example, replaces point particles with one-dimensional strings whose vibrations create both matter and forces. In this framework, gravity emerges naturally as one of the possible vibration modes of a string. Loop quantum gravity, by contrast, keeps space-time itself but discretizes it, turning the smooth geometry of Einstein into a network of finite loops and nodes. Each loop represents a tiny quantum of area or volume. Both approaches aim to describe how space and time behave when divided into their smallest possible units, at scales around 10 to the power of -35 meters, the Planck length. At that scale, our familiar notions of distance and duration lose their meaning. Space-time may no longer be continuous, but frothy and uncertain, a quantum foam of ever-changing geometry. Einstein's equations cannot be trusted there, for they predict singularities where curvature becomes infinite. Quantum theory, on the other hand, demands finiteness. Somewhere in the union of these two lies a new theory, one that must reduce to general relativity at large scales and to quantum mechanics at small scales. The pursuit of this theory is not just mathematical curiosity. It is the attempt to understand what reality truly is. If gravity can be shown to have a quantum nature, then space and time themselves must be built from discrete information. The universe would not be a continuous expanse, but a coded structure, a cosmic computation. Every particle, every field, every interaction would be part of an informational web that gives rise to geometry and motion. The more scientists explore, the more gravity seems to whisper that it is not what we think. It is at once everywhere and almost nothing, binding galaxies but too faint to bind 2 grains of sand on a table. Its weakness makes it subtle, yet its reach makes it absolute. Perhaps that is the secret, that gravity is not a separate entity, but the echo of all other things combined. The curvature of space-time might be a reflection of the universe's information content, the total bookkeeping of matter, energy, and entropy. To approach this idea is to stand on the edge of knowledge itself. One side is the smooth continuum of Einstein's cosmos. The other is the discrete quantum world of uncertainty and entanglement. Between them lies a gulf we have not yet crossed. But if we ever find the bridge, if we can show that gravity, too, is quantum, we will not just understand the force that binds the stars. We will understand why there is a fabric of reality at all. Every idea in physics eventually faces its limit. Newton's laws broke under the speed of light. Einstein's curved space-time breaks at the edge of a black hole or the beginning of the universe, and the quantum rules that govern atoms cannot yet tell us what happens when space itself trembles. The frontier where gravity and quantum mechanics meet is not just a boundary of knowledge, it is a boundary of imagination. To reach that frontier, we must shrink the universe in our minds. Picture the Earth reduced to a marble, then to a grain of sand, then smaller still, until it becomes an invisible point. The gravitational field of that point does not vanish. It grows infinitely strong. The equations of general relativity say the curvature of spacetime there becomes infinite, forming what we call a singularity. But infinity is not a physical number. It is a signal that the theory has failed. Nature never produces infinities. Our mathematics does. Somewhere beneath that failure, another description must exist, one that makes sense of the impossible. When we imagine spacetime at the Planck scale, about 10 to the power of minus 35 meters, we step into a world where distance and time cannot be divided further. The very concept of before and after begins to dissolve. Particles may appear connected across vast separations, as if distance itself were an illusion. In that realm, gravity cannot remain smooth and continuous. It must fluctuate, jittering with the same uncertainty that rules electrons and photons. Physicists have tried to picture this. Some imagine spacetime as a network of quantum connections, tiny loops of geometry woven together like threads in a fabric. Others see it as a vibrating symphony of strings, each tone representing a particle, with gravity emerging from one special note, the string vibration that carries spin 2 and no mass. Both visions point to a universe that is not continuous but digital, not static but dynamic at the smallest possible level. If we could zoom in to those scales, we would not see space as emptiness. We would see a storm of energy flickering in and out of existence, virtual particles forming and vanishing too fast for light to notice. The smooth void between stars is not empty, but alive with possibility. Gravity, in this view, may be the large-scale echo of that storm, the averaged effect of countless quantum fluctuations. Our inability to see these fluctuations is not a failure of imagination, but of scale. The gravitational pull between two electrons is so weak that even if we magnified it trillions upon trillions of times, it would still be smaller than a whisper. Detecting a single graviton, the smallest quantum of gravity, would require an instrument larger than Jupiter and colder than the cosmic background itself. Even the most sensitive detectors on Earth, such as the LIGO observatories, that can sense distortions in spacetime smaller than a fraction of a proton's width, are blind to individual quanta of gravity. Still, the search continues. We look for subtle clues, how gravity might entangle tiny masses, how it could create correlations between quantum systems that no classical field could explain. Some experiments aim to suspend microscopic mirrors or spheres in superposition, allowing them to feel each other's gravitational pull through quantum interference. If such an effect were observed, it would be evidence that gravity itself carries quantum information. Until that day, we are left with two great theories that work perfectly in their own domains, but refuse to speak to each other. Einstein's gravity describes the structure of the universe on the largest scales. Quantum mechanics governs the behavior of everything on the smallest. Each is complete in itself, yet together they produce contradictions so deep that even the meaning of space and time becomes uncertain. The universe does not care about our mathematical divisions. Stars collapse, black holes evaporate, the cosmos expands. Somewhere, the rules that govern all these events must be unified. Perhaps gravity is quantum, and we have not yet found its particles. Perhaps it is emergent, a shadow cast by deeper laws of information. Or perhaps it is something we have not imagined at all. What we do know is that the story of gravity is not finished. The same force that draws an apple to the ground also shapes the flow of galaxies across billions of light years. The same geometry that bends starlight near the sun also determines the destiny of the cosmos. And beneath it all, hidden in the trembling at the smallest scales, may lie the secret of why there is a universe instead of nothing. If every other force is quantum, why not gravity? That question lingers like a chord unresolved. It is the doorway to everything that follows. The search for the graviton, the mystery of the Planck scale, and the hope that one day we will see space-time itself not as a stage, but as the shimmering dance of quantum information. The closer we look at nature, the stranger it becomes. What once seemed smooth and solid turns out to be restless and uncertain. The walls of matter dissolve into fields that ripple and interfere like water on a wind-stirred lake. Beneath every atom, beneath every grain of dust, lies a world ruled not by certainty, but by probability, a world where events do not happen until they are observed. This is the quantum world, the invisible foundation of everything that exists. It began with light. In the early 1900s, physicists believed light was a wave, spreading continuously through space like ripples on a pond. Then came the experiments of Max Planck and Albert Einstein, who showed that light could also behave like a stream of particles, each carrying a discrete packet of energy. They called these packets photons, and they revealed a truth far deeper than anyone expected. Energy, it seemed, did not flow smoothly, but arrived in jumps, in quanta. The universe was not continuous but quantized. This discovery changed everything. Matter itself began to show the same dual nature. Electrons could behave like particles when striking a screen, yet like waves when passing through slits. Atoms, once imagined as tiny solar systems with electrons circling a nucleus, were found to be probability clouds, regions where an electron might be found if measured, but never with absolute certainty. The equations of quantum mechanics did not describe where things are, only the chances of where they might be. The strangeness deepened. When two particles interact, their properties become linked in a way that defies classical intuition. Measure one, and you instantly affect the other, no matter how far apart they have drifted. This connection, called entanglement, was so disturbing that Einstein called it spooky action at a distance. Yet countless experiments have proved it real. Quantum mechanics shows us a universe in which information, not location, defines reality. At its heart, quantum theory is built on the concept of fields. A field is not a thing in space. It is what space is filled with. The electromagnetic field, for instance, pervades all of space. Its excitations are photons. The electron field gives rise to electrons, the quark fields to quarks. Every particle is a vibration of an underlying field, and every interaction is an exchange of quanta between fields. When we speak of forces in the quantum world, we mean the transfer of energy between these excitations. In this picture, the universe becomes a grand orchestra of vibrations. Photons mediate the electromagnetic interaction. Gluons carry the strong force that binds quarks inside protons and neutrons. The W and Z bosons mediate the weak force responsible for radioactive decay. Each force has its own messenger, its own quantum of interaction. The mathematics that describes all this, the quantum field theory, has predicted phenomena to a precision unmatched in any other science. It has been tested in particle colliders, in lasers, and in the subtle behavior of electrons in magnetic fields. Yet, amid this triumph, one force stands apart. Gravity. The pull that holds us to the Earth and guides planets around the Sun refuses to fit into this quantum symphony. If gravity were like the other forces, it should have its own messenger particle, a graviton, mediating its effects in discrete quanta. But we have never seen such a thing, not even a hint of it. Every attempt to describe gravity in the same quantum language leads to equations that blow up into infinities. Why does gravity resist quantization when every other force obeys it? Perhaps it is because gravity does not act within space and time. It is space and time. In Einstein's general relativity, gravity is not a field within spacetime, but the curvature of spacetime itself. Trying to apply quantum rules to it is like trying to describe the vibrations of a drum while the drumhead itself is changing shape beneath your hands. Still, the dream of unification persists. We cannot imagine a universe where quantum and gravity remain forever separate. Somewhere, at some scale, they must merge into one coherent description. After all, black holes exist, and they combine enormous gravitational fields with intense quantum effects. The early universe, too, was a furnace where quantum fluctuations in space-time gave birth to galaxies. The cosmos itself is a witness to the quantum nature of reality. even if we do not yet have the language to express it. Quantum theory tells us that emptiness is never truly empty. Even in a perfect vacuum, fields fluctuate, creating pairs of virtual particles that appear and disappear in moments too short to measure. These fluctuations are not theoretical guesses. They have measurable effects, such as the slight attraction between metal plates known as the Casimir force. The void is alive, its energy woven into the fabric of space-time. Gravity, too, must feel this restless sea. At the quantum level, uncertainty is not a limitation of measurement, it is a property of existence. You cannot know both the position and the momentum of a particle with absolute precision. You cannot predict the exact instant when a radioactive atom will decay. The universe is not deterministic in the way Newton imagined. Instead, it is probabilistic, a great cosmic dice game where the rules of chance are written in the mathematics of the wave function. If the quantum world feels strange, it is only because we are creatures of the macroscopic realm. The probabilities average out at large scales, giving us the illusion of solidity and certainty. But beneath every rock, every breath of air, and every beam of starlight, the quantum rules hold sway. The fact that we can predict the behavior of an electron with astonishing accuracy is proof not of chaos, but of an underlying order deeper than our senses can grasp. Quantum mechanics has been tested in every possible way and never found wanting. It explains the color of stars, the chemistry of life, the working of computers, and the stability of matter itself. Without it, atoms would collapse, and no structure in the universe could survive. The quantum world is not distant or abstract. It is the reason we exist. And yet, despite all its triumphs, quantum mechanics still leaves us uneasy. It describes how things happen, but not why they happen that way. It gives probabilities but hides the mechanism. It shows us patterns of immense precision without revealing the underlying cause. This sense of incompleteness mirrors the tension we feel with gravity. Both are astonishingly accurate, yet neither tells the whole story. To bridge them, we must look beyond particles and forces to something deeper, perhaps information itself. For if every quantum event encodes information, and gravity shapes the geometry in which that information flows, then the two may not be separate at all. They may be two sides of one coin, one describing energy, and the other describing the stage upon which energy acts. In this way, the quantum world hints that the universe is not made of matter or even fields, but of relationships, probabilities, and information. It is a world where being and knowing are intertwined, where observation becomes creation, and where the smallest flicker of energy might contain the blueprint of space-time itself. And so the question remains, if every force in nature is quantum, where is the quantum face of gravity? The answer may lie in a particle we have never seen, a messenger that whispers across the curvature of space-time, the missing graviton. At the foundation of quantum theory lies an idea that stretches our language almost to breaking. Everything that exists is not truly a thing, but a pattern of probability. Matter, light, energy, and even emptiness are made of the same mysterious fabric. Fields that pulse and fluctuate. A field fills all of space, invisible yet ever present. It is not confined to any location. Instead, what we call a particle is a tiny region where the field's vibration concentrates for a moment before dissolving again into possibility. This view replaced the tidy mechanical universe of the 19th century with one built from uncertainty. If you look for an electron's position, you blur its momentum. If you know its energy precisely, you lose its time of existence. These are not flaws of measurement, but the very grammar of nature. The quantum rules do not care about human expectations. They speak in probabilities that, when added up over many events, form the world of predictable physics we live in. Each type of field follows its own rhythm. The electromagnetic field sings in photons. The quark field hums in triplets bound by gluons. The weak field shivers through heavy W and Z bosons that appear only in high-energy collisions. The mathematical structure that unites these songs is elegant beyond belief. Quantum field theory has predicted the magnetic moment of the electron to more than 10 decimal places, a precision no other theory in science has matched. When the results of colliders and cosmic measurements are compared to its equations, they fit as perfectly as pieces of glass. But within this triumph lies a silence, the field that bends starlight, that curves the paths of planets, and slows the ticking of clocks, refuses to join the orchestra. Gravity behaves as though it plays by another set of rules entirely. It acts not inside space and time, but upon their shape. When physicists attempt to write a quantum field equation for gravity, the sums diverge into meaningless infinities. It is as if the stage of the cosmic performance cannot be quantized because it is the stage. This puzzle has drawn generations of thinkers. Some suspect that space-time itself might be built from quantum threads so fine that they blur into a continuum at our scale. Others believe gravity may not be fundamental at all, but a kind of collective behavior emerging from microscopic information. Whichever answer proves true, the bridge between quantum theory and Einstein's geometry will change how we see everything. To imagine how these worlds might meet, picture an atom suspended in the darkness of interstellar space. Its electron cloud trembles with uncertainty, while far away a star's gravity curves the surrounding spacetime. The two phenomena seem unrelated, yet both describe how energy shapes reality. Perhaps they are different expressions of the same deeper principle, a principle that binds geometry and probability into one whole. In quantum mechanics, reality is not fixed until it interacts. Observation is participation. The act of measurement selects a single outcome from the cloud of possibilities. Some interpretations suggest that the entire universe is one vast wave function still unfolding, with every measurement a small collapse of potential into fact. Gravity, in this light, might be the large-scale trace of that process, the geometry written by the sum of all quantum interactions. To test such ideas, we need to bring gravity into the laboratory of the quantum. That means building experiments delicate enough to let massive objects exist in superposition, or to detect correlations between distant systems that could only have arisen through a gravitational quantum link. If gravity can entangle, it must be quantum. If it cannot, our entire understanding of space-time must change. As our instruments become ever more precise, the line between quantum mechanics and general relativity grows thinner. Tiny resonators vibrate near absolute zero, mirrors float on laser beams, and atomic clocks tick with accuracies that can sense the difference in gravity between a table's top and bottom. Each new advance brings us closer to seeing how the smallest quanta of information might weave the largest fabric of space. In the quantum world, emptiness is alive, forces are exchanges of information, and the act of observing reshapes the story. Gravity's refusal to fit into this picture is not a failure, but an invitation. Somewhere in the mathematics of uncertainty lies the key to understanding why the universe has structure, why time flows, and why there is something rather than nothing. To find that key, we must search for the missing note in the cosmic symphony, the graviton, the hypothetical particle of gravity that no one has yet heard. In the silence between stars, space seems empty, but quantum theory whispers that it is anything but. The vacuum boils with invisible energy, flickers of creation and annihilation that happen faster than thought. These momentary births and deaths of virtual particles fill every corner of the cosmos. They cannot be seen directly, yet their effects are measurable. The pressure they create shifts the energy of atoms, bends light, and may even push the expansion of the universe itself. The void, far from being nothing, is the restless heart of everything. This sea of fluctuations means that even space has a kind of texture, a graininess that we cannot yet resolve. When gravity enters this picture, the concept of a smooth continuum begins to falter. If energy and momentum are uncertain, then so is the curvature of space-time that depends on them. The very geometry of the universe must tremble with quantum uncertainty. But in Einstein's equations, geometry is exact, continuous, and deterministic. Reconciling these two descriptions is like trying to merge a painting of clouds with a photograph of fog. They describe the same thing in different languages. Quantum mechanics and general relativity each hold half the truth. The quantum world shows us that energy comes in discrete quanta, that particles exist as probabilities, that measurement defines outcome. Relativity shows us that mass and energy curve the geometry of space-time, that motion and gravity are indistinguishable, and that time itself flows differently for different observers. Both theories are spectacularly successful, and both break down when pushed to their extremes. At the heart of a black hole, or in the first moments of the Big Bang, their predictions clash. One speaks of smooth curvature, the other of discrete quanta. Somewhere, a deeper theory must reconcile the two. Physicists have long searched for a bridge. The standard model of particle physics unifies the electromagnetic, weak and strong forces into a single framework of quantum fields, but gravity stands outside it. In the equations of the standard model, spacetime is a fixed background, a stage on which particles dance. In Einstein's theory, the stage itself bends and twists. To make gravity quantum, we would need a theory in which spacetime is not fixed, but dynamic, fluctuating, and quantized like everything else. Some imagine that this quantization would give rise to a new particle, the graviton. In that picture, the gravitational field is made of countless tiny quanta, each carrying the faintest possible pull. These quanta would interact with matter in a way so subtle that we have never noticed them. Detecting even one would require an experiment spanning planets, for gravity's coupling is so weak that it fades into the noise of every other interaction. Yet, if gravitons exist, they would complete the symmetry of physics. Every force would have its quantum messenger. The challenge is that gravity operates on scales vastly larger than those of quantum mechanics. To observe its quanta, we would have to probe distances near the Planck length, around 10 to the power of minus 35 meters. That is a trillion times smaller than an atom. No instrument can reach it, and no energy on Earth can recreate its conditions. Even the most powerful colliders, smashing particles at trillions of electron volts, fall short by many orders of magnitude. We can see gravity's effects on galaxies, but not on quanta. Still, there are hints. In the mathematics of quantum field theory, any force that propagates through space must have a quantum particle associated with it. Gravity, if treated this way, would produce a spin 2 particle with zero mass, exactly what a graviton would be. The idea fits beautifully, yet the infinities remain. Calculations of graviton interactions explode into divergences that no renormalization can tame. Unlike the other forces, gravity's strength grows with energy, so at high energies the theory devours itself. This is the core of the problem. The smoothness of spacetime cannot survive the churning chaos of the quantum world without tearing apart. Perhaps then, the question is not how to quantize gravity, but how to make spacetime itself emerge from quantum principles. What if space and time are not fundamental, but byproducts of entanglement, relationships between bits of quantum information? In that case, gravity might not need a particle at all. It might be a large-scale illusion born from microscopic correlations, the way temperature arises from countless molecules moving at random. This idea is daring, but it fits a pattern that physics has shown us again and again. What we see as continuous is often the sum of discrete parts. Sound is the collective motion of molecules. Heat is the average of kinetic energy. Light is a stream of photons. Why not gravity as the statistical behavior of deeper quantum constituents of spacetime itself? Whatever the answer, the implications are enormous. To discover the quantum nature of gravity is to discover what space and time truly are. Are they fundamental, or do they emerge from something else? Is the universe a geometric continuum, or a vast network of quantum connections weaving themselves into a tapestry we call spacetime? As we search for the graviton, we are really searching for the meaning of existence at its deepest level. The next step in that search will lead us to the edge of known physics, to the smallest possible scale where gravity and quantum mechanics can no longer be separated. The Planck scale, where the universe's smooth surface gives way to a foaming sea of uncertainty. If gravity is truly a force like the others, it should have a messenger, a quantum particle that carries its pull through space. Just as photons carry light and gluons hold atomic nuclei together, gravity's whisper should come from a single, elegant vibration, the graviton. It is a simple idea, and yet, after more than a century of searching, not a single graviton has ever been seen. The graviton is the ghost of physics. The equations predict its existence so naturally that it feels inevitable. A massless particle with spin 2, moving at the speed of light, it would be the smallest possible unit of gravitational energy. It would ripple through spacetime, the way a photon ripples through the electromagnetic field. Every gravitational wave would be made of countless gravitons, each one carrying an infinitesimal fragment of curvature. If they exist, they should fill the universe, streaming endlessly from stars, black holes, and the first moments after the Big Bang. But gravity is weak, unimaginably weak. Between two protons, the gravitational attraction is about 40 orders of magnitude weaker than their electromagnetic repulsion. In ordinary terms, this means that the gravitational pull between two particles is smaller than a whisper compared to a hurricane. To detect a single graviton, we would need an instrument so massive that it would collapse into a black hole under its own gravity before it could even begin the measurement. Nature herself seems to forbid the experiment. The detectors we have built can sense the trembling of space-time from merging black holes billions of light years away. Yet what they detect are classical waves, collective vibrations of space-time, not individual quanta. The LIGO observatories, with arms 4 kilometers long, measure changes in distance smaller than a fraction of a proton's width. But even they cannot hope to register the arrival of a single graviton. The effect would be smaller than the uncertainty of the measuring device itself. This strange limitation raises a deeper question. If a particle can never be detected, does it truly exist? In the quantum world, we are used to things being invisible, yet real, inferred through their effects. We cannot see electrons directly, but we can measure their charge. We cannot see neutrinos, but we can watch them strike atomic nuclei. The graviton, however, leaves no trace that we can isolate. Its influence blends completely with the curvature of space-time. It may be everywhere, yet forever beyond our reach. Mathematically, the graviton fits neatly into quantum field theory. It appears automatically when we linearize Einstein's equations. That is, when we treat space-time as nearly flat and allow small ripples to propagate through it. These ripples behave like waves, and in quantum language, waves correspond to particles. The problem is that this approximation breaks down when gravity becomes strong. Near black holes or at the birth of the universe, the ripples are no longer small. The full, non-linear structure of general relativity takes over, and the quantum description fails. Gravity resists being tamed by the same methods that work for the other forces. If we calculate how gravitons should interact with one another, the results quickly spiral into infinities that cannot be cancelled. Every attempt to renormalize the equations, to absorb those infinities into measurable quantities, fails. Unlike the electromagnetic field, which behaves smoothly at small scales, the gravitational field grows uncontrollably strong. The more we zoom in, the wilder it becomes. At the Planck scale, the mathematics breaks apart entirely, suggesting that space-time itself loses meaning. Still, the idea of the graviton persists because it carries a certain elegance. It allows us to imagine gravity as just another quantum field, a vibration like all the rest. It preserves the symmetry of nature, giving every force a corresponding particle. Even if we cannot detect it directly, the graviton serves as a conceptual bridge, a way to connect the language of Einstein with the language of quantum theory. If gravitons exist, they must be all around us. Every time a mass moves, every time a planet shifts in its orbit, it sends out an endless shower of them. They would pass through our bodies and through the Earth without resistance, slipping through matter as if it were transparent. Trillions upon trillions would cross each square meter every second, yet none would leave a mark. We are immersed in a sea of invisible quanta, carrying the curvature of the cosmos from one end to the other, and we cannot feel them at all. There is something poetic about that. The idea that the most universal force in nature might be composed of particles that can never be seen, never caught, never touched. The graviton may be not only undetectable, but also unnecessary, a sign that we are trying to describe a geometric truth with the wrong vocabulary. Maybe gravity is not a field living inside spacetime, but the shape of spacetime itself. To speak of gravitons might be like speaking of atoms of curvature, useful for imagination, but not fundamental. Yet even if the graviton is only a mathematical ghost, it guides us toward the deeper unity we seek. It tells us that gravity should, in principle, behave like every other force at the smallest scales. Somewhere below the smooth surface of spacetime, there must be a quantum structure that gives rise to curvature. The absence of the graviton in our detectors is not the end of the story, but the beginning of a question. What is spacetime made of? If we could answer that, we would understand why gravity is so weak, why it resists quantization, and why the universe looks the way it does. For now, the graviton remains missing, a phantom particle at the intersection of two great theories. But to search for it is to search for the fabric of reality itself, and that search leads us to the smallest scales imaginable, to the Planck realm, where gravity and quantum mechanics must finally meet. The graviton remains a theory wrapped in hope. We imagine it because the pattern of nature demands symmetry, because it would make the language of physics universal. Yet the more we look for it, the more gravity behaves as if it is something else entirely, not a simple particle in a field, but a feature of the universe itself. When Einstein described spacetime as curved, he did not need a messenger. The geometry of the universe was enough. Matter told spacetime how to curve, and that curvature told matter how to move. But if we insist on quantizing that curvature, then at the smallest scales, the geometry must break into quanta, into tiny vibrations. These would be the gravitons, each one a discrete twist in the weave of space and time. The trouble is that spacetime does not lend itself easily to division. It is like trying to slice a horizon or weigh a shadow. Physicists have long tried to catch gravity's quantum echo indirectly. They study the cosmic microwave background, the faint light left over from the birth of the universe. Tiny irregularities in that ancient radiation might bear the imprint of primordial gravitational waves, ripples created when the cosmos was less than a trillionth of a second old. If those ripples were quantized, they would have been made of gravitons. Detecting their pattern would be the first sign that gravity obeys quantum rules. So far, the signals are too faint, lost in the noise of galactic dust and cosmic expansion. Still, every attempt brings us closer to the limits of measurement. Experiments like BICEP and Planck have mapped the sky's polarization to extraordinary precision, revealing whispers of those ancient ripples, but the signature of quantum gravity remains uncertain. Perhaps we are looking in the wrong place. Perhaps gravitons, if they exist, do not travel freely through space, but dissolve into the fabric that created them. Or perhaps gravity is not a field within space at all, but a manifestation of space's existence. Imagine spacetime as a vast ocean. The waves that roll across it are gravitational waves, which we can detect. But the molecules of that ocean, the quanta that make it up, remain invisible. The graviton would be one of those molecules, but we can neither isolate nor count them. Our detectors measure the collective swell of the sea, not its individual drops. To sense a graviton directly would require interacting with it one-on-one, but the energy of a single graviton is so minute that any device sensitive enough to measure it would collapse under its own gravity before it could record the event. The act of detection would destroy the observer. This paradox tells us something profound about the nature of the universe. The same equations that predict the graviton also show why it hides from us. Gravity is self-interacting. It couples to all forms of energy, including its own. This makes it inherently nonlinear. The very act of describing it as a quantum field introduces the seeds of its own collapse. The graviton, if real, is the messenger that cannot be separated from the message. Some physicists have suggested that the graviton might not exist at all, that quantizing gravity is like trying to count the threads in a mirage. Instead, they propose that spacetime itself is emergent, a phenomenon that arises from the statistical behavior of something deeper, perhaps quantum information, perhaps entanglement. In that view, gravity is not carried by a particle, but by the pattern of relationships among quantum states. It is not transmitted through space. It is what makes space possible. Yet, despite the elegance of these ideas, the graviton refuses to fade from theory. It appears naturally whenever we treat gravity as a small perturbation of flat spacetime. It explains how gravitational waves can propagate and how energy can be exchanged through curvature. It gives us a vocabulary for describing the quantum aspects of the universe's most ancient force. Even if we never find it, it remains a useful ghost, guiding us toward the quantum structure that must exist beneath Einstein's smooth geometry. If someday we could harness a detector beyond imagination, capable of sensing a single graviton without collapsing under its own weight, what would we see? Perhaps nothing. Perhaps the detection itself would prove that spacetime is not made of particles at all, but of something stranger. Or perhaps we would catch a faint pulse, a whisper of curvature quantized, and know at last that the force shaping the stars and bending light is woven from the same quantum threads as everything else. For now, the graviton remains missing, an idea suspended between possibility and myth, but its absence does not diminish its importance. It stands as a challenge, reminding us that our understanding of the universe is still incomplete. To find it, or to prove that it is not needed, we must journey deeper to the boundary where gravity itself becomes quantum, to the Planck scale where spacetime dissolves into foam and the familiar laws of nature lose their meaning. At the edge of understanding lies a horizon that no instrument can cross, the scale where gravity and quantum mechanics must finally meet. Physicists call it the Planck scale, a realm so small and energetic that our current theories lose coherence. To reach it would require compressing a single particle of light into a region smaller than 10 to the power of -35 meters, an act that would create a miniature black hole and seal the information within. It is the ultimate frontier, where the smooth curves of Einstein's geometry crumble into a storm of quantum fluctuations. The graviton, if it exists, must dwell there. Each one would represent a ripple in the quantum foam of spacetime, a grain of curvature beyond all resolution. But because gravity becomes overwhelmingly strong at that scale, every attempt to probe it leads to collapse. The observer cannot separate from the observed. Energy concentrated enough to reveal the structure of spacetime destroys that structure in the process. This is why no telescope or collider can ever see a graviton. Nature draws a curtain at the Planck length, beyond which our current mathematics cannot go. Yet that invisible boundary is where the answers must lie. It is the birthplace of black holes, the dawn of the universe, the region where the laws of the large and the laws of the small are forced to coexist. In the earliest fractions of a second after the Big Bang, the entire cosmos was smaller than a proton and hotter than 10 to the power of 32 degrees Celsius. Gravity and quantum mechanics could not have been separate there. They must have merged into one. Somewhere in the relic radiation of that age, the quantum fingerprints of gravity still linger. Physicists search for those traces in the cosmic microwave background, in the polarization of ancient light, in the subtle pattern of gravitational waves stretching across the sky. A confirmed detection of primordial gravitational waves would be indirect proof that gravity is quantum, for only quantized fluctuations could leave that pattern. So far, the evidence remains elusive, but the pursuit itself has reshaped cosmology, leading to new instruments and new insights into how the universe began. At the same time, theorists continue to refine their models. Some imagine that gravitons interact not through the familiar four dimensions of space and time, but through hidden ones curled up beyond our perception. In these higher dimensional models, gravity's apparent weakness could be an illusion, its strength diluted across extra dimensions. Others propose that gravitons could leak from our universe into a larger multiverse, carrying information in ways we cannot yet detect. Whether or not these ideas are true, they remind us that gravity may be more than a force. It may be the architecture of reality itself. Despite our ignorance, there is reason for optimism. The fact that the universe is comprehensible at all, that mathematics written on paper can describe the motions of galaxies and the behavior of electrons, suggests that a deeper unity exists. The missing graviton is not just a gap in our knowledge, but a clue that points toward that unity. Every failed experiment, every divergence in the equations, tells us where the limits of our current theories lie, and where new ones must begin. If gravity truly has a quantum nature, then the geometry of spacetime must be built from information. Each tiny region would encode the way it interacts with its neighbors, forming a web of relationships rather than a continuous substance. The graviton would then be not a particle in space, but a fluctuation of that informational network, a change in the pattern that defines what space is. In this vision, the universe becomes a self-organizing system, a vast computation where the laws of physics are the rules by which information transforms. The search for the graviton is therefore not only a quest for a particle, but a quest for meaning. It forces us to ask whether space and time are fundamental or emergent, whether reality is continuous or discrete, whether the universe is a machine or a code. Each possibility reshapes how we see ourselves in the cosmos. If space-time is a product of quantum information, then every atom, every photon, and every heartbeat participates in the same universal computation. Gravity would not merely hold us to the Earth, it would connect us to the structure of existence itself. And so, the graviton, unseen, undetected, and perhaps unknowable, becomes a symbol of the mystery at the core of physics. It stands at the threshold between the known and the unimaginable, between the classical and the quantum. Whether it turns out to be real or only a metaphor for a deeper truth, its pursuit drives us toward the Planck scale, where gravity becomes quantum and the universe reveals its smallest, most secret face. There is a frontier in physics where all familiar ideas collapse. Space and time lose their smoothness. Matter and energy blur together. Even causality begins to tremble. This is the Planck scale, the boundary where the fabric of space-time unravels into something restless and unknown. To speak of this scale is to speak of limits, of distances so small, time so brief, and energy so immense that the very language of science begins to fail. The Planck length, about 10 to the power of minus 35 meters, is the smallest distance that has any physical meaning. Below it, the concept of location disappears. If one were to probe such a tiny region with a photon of sufficiently short wavelength, the energy of that photon would be so great that it would curve space-time around itself, creating a black hole and hiding the very thing it was meant to reveal. The observer and the observed would collapse together, leaving only a trembling patch of curved geometry. This is nature's way of saying no further. At the same scale, there is the Planck time, roughly 10 to the power of minus 43 seconds, the shortest possible duration. It marks the boundary where time itself ceases to flow in a continuous stream. The Planck energy, about 10 to the power of 19 giga-electron volts, is the amount required to confine one particle to that unimaginably small distance. These numbers define the scale at which gravity must become quantum, because any attempt to measure beyond them turns space-time into a foam of uncertainty. Imagine space-time not as a smooth sheet, but as a sea of bubbles constantly appearing and vanishing. Each bubble represents a fluctuation, a tiny warp in geometry, a burst of energy borrowed and repaid in a moment shorter than Planck time. The calm fabric we see on cosmic scales is only the average of this chaos. Just as a lake looks flat from far away but reveals waves and spray up close, space-time itself may hide a storm beneath its surface. This concept of quantum foam was first envisioned by John Wheeler, who saw space-time as a living, dynamic structure rather than a static backdrop. In his view, even empty space is not truly empty. Virtual black holes form and evaporate endlessly, twisting and reconnecting the geometry of the universe in an eternal dance. To the human mind, it is a realm beyond visualization, where distances cannot be measured and events have no clear order. Cause and effect may even trade places in the maelstrom. At this frontier, Einstein's equations collapse under their own weight. The curvature of space-time, which they describe so beautifully on larger scales, grows without bound at small ones. Quantum mechanics, meanwhile, insists that energy and momentum can never be known precisely. Combine the two, and the result is a landscape of infinite curvature and infinite uncertainty, a paradox that no existing theory can resolve. Something new must take over, a deeper law that unites geometry with quantum behavior. This is the region physicists call the Planck domain. It is not a place we can visit, but a boundary that lies at the foundation of all things. Every particle, every interaction, every wave of light originates from it. When the universe was born, it was entirely governed by Planck-scale physics. In that first fraction of a second, space-time itself was still crystallizing from the quantum foam. As the cosmos expanded and cooled, the smooth continuum we now inhabit emerged, like ice forming from turbulent water. To understand gravity as a quantum phenomenon, we must understand what happens in that transition, how the granular structure of space-time averages into the smooth geometry of relativity. It is like asking how the motion of countless molecules gives rise to the flow of air, or how the interactions of atoms in a crystal produce sound waves. But here, the molecules are bits of space-time itself, and their collective behavior defines what we mean by distance, direction, and duration. No experiment today can reach the Planck scale directly. The energies required are beyond anything nature has produced since the Big Bang, except perhaps near the heart of black holes. But the clues may still be visible in the universe around us, in the spectrum of gravitational waves, in the pattern of cosmic inflation, or in the subtle deviations of light as it travels across billions of light years. If space-time has a discrete structure, those imprints may one day betray its grain. The Planck scale is therefore not only a limit of measurement, but a doorway. It marks the point where the familiar dissolves into the unknown, where geometry becomes probability, and where the gravitational field reveals its quantum face. It is here that theories like loop quantum gravity, string theory, and emergent gravity all converge, each offering a different picture of what space-time might be made of. Beneath the calm surface of the cosmos, there may lie a lattice of quantized geometry, each tiny unit representing a finite chunk of area or volume. Or there may be vibrating strings whose harmonics give rise to all forces and particles. Or perhaps the true foundation is not geometric at all, but informational, a network of entanglements that generate both space and time from pure relationship. Whatever the answer, the Planck scale is where that mystery begins. The journey to understand it is not merely scientific, but philosophical. It asks whether reality is continuous or discrete, deterministic or probabilistic, objective or relational. At this smallest of all scales, the universe might not be a thing, but an algorithm, a process that computes its own existence moment by moment. And if that is true, then gravity, the curvature of spacetime, is not a force at all, but the emergent pattern of that cosmic computation. Beyond the Planck length, our mathematics dissolves into paradox. Yet it is precisely there, in the place where everything breaks, that new physics must be born. For the universe cannot be infinite in its smallness, any more than it can be infinite in its vastness. Somewhere between the quantum and the cosmic, the code of reality must repeat, closing the circle that unites the large and the small. At the Planck scale, the universe no longer behaves like a smooth continuum, but like a restless sea of uncertainty. Every point in space becomes an arena of violent fluctuation, every instant of time a storm of creation and annihilation. The calm geometry of Einstein's cosmos dissolves into a fog of possibility. In this fog, the difference between matter and energy, between space and time, even between cause and effect, begins to blur. Imagine trying to measure a distance smaller than 10 to the power of -35 meters. The light needed would carry such immense energy that it would warp the very space-time it was meant to illuminate. The act of measurement would create a gravitational well deeper than the region being observed. The probe would vanish behind its own event horizon, leaving no information behind. In this way, nature sets a fundamental limit on resolution. Below the Planck length, measurement becomes meaningless. John Wheeler called this realm the quantum foam. It is not made of matter, but of geometry itself. Tiny bubbles of space-time continually appear and disappear, stretching and reconnecting in patterns that defy visualization. The topology of the universe, the way its dimensions are connected, may change from moment to moment. Wormholes might form spontaneously, linking distant regions before collapsing again in a whisper of quantum turbulence. Space is no longer the stage upon which events unfold. It is one of the actors. At this scale, the energy density of a single fluctuation can reach values so extreme that gravity becomes as strong as any other force. The smooth fabric of spacetime predicted by general relativity cannot survive such violence. Einstein's equations rely on differentiability, on the idea that curves can be drawn with infinite precision. Quantum mechanics forbids this. Every attempt to calculate curvature at the Planck length produces infinities, signaling that the geometry is no longer continuous. The universe, at its core, may be built from discrete elements, tiny quanta of area and volume, woven together into the appearance of continuity. Loop quantum gravity takes this idea seriously. It proposes that spacetime itself is quantized, made of finite loops forming a vast network called a spin foam. Each loop represents the smallest possible unit of area, each node a tiny grain of volume. Together they create a dynamic lattice that vibrates and evolves, giving rise to the geometry we perceive. In this picture, space is not empty. It is a web of relationships, a fabric stitched from pure quantum connection. Gravity is not a separate force, but the curvature that emerges when these loops twist and stretch. String theory offers another vision. It replaces the point-like particles of quantum field theory with one-dimensional strings whose vibrations determine what they are. Different modes of vibration correspond to different particles: electrons, photons, quarks, and even the graviton. The beauty of string theory is that gravity arises naturally from it. The vibration that corresponds to a spin 2, massless particle appears unavoidably, but strings can only make sense in higher dimensions. According to the mathematics, the universe must have more than the 4 dimensions we experience. The extra ones are compactified, curled up at the Planck scale, hidden from view yet influencing the behavior of everything we see. Both loop quantum gravity and string theory attempt to describe the same truth, that space-time is not fundamental but emergent. They differ in method and in emphasis, but they share a vision of discreteness. Beneath the continuum of general relativity lies a quantum structure, a realm where geometry itself is granular. At macroscopic scales, the grains are so fine that they blend together, just as individual water molecules blend into the smooth surface of a wave. If we could somehow peer into this realm, what would we see? Perhaps a frothing expanse of bubbles, each one a fragment of space-time flickering into existence for a heartbeat of Planck time. Perhaps a vibrating web of strings, their harmonics resonating across hidden dimensions. Or perhaps we would see something even stranger. No space, no time, only pure relationships, patterns of information connecting everything to everything else. Relativity fails here because it assumes continuity. Quantum mechanics fails because it assumes a background in which probabilities evolve. But at the Planck scale, there is no background. The geometry itself is uncertain. We cannot say where or when an event occurs because where and when have not yet crystallized into meaning. Only when many such quantum events combine does space-time emerge as an approximate concept. The classical world we experience is not fundamental. It is an average, the shadow cast by countless microscopic interactions. This view transforms our understanding of gravity. It is not a force transmitted through space, it is the large-scale pattern of space itself. The curvature that bends starlight and guides planets is the echo of countless quantum processes beneath the surface. To grasp the Planck scale is to see that the universe is built not from things, but from interactions, from information exchanged among the smallest conceivable elements of reality. In that sense, we are all made of geometry, not of matter in space, but of space becoming matter. Every atom, every photon, every heartbeat arises from the same quantum fabric, woven anew each moment. The Planck scale is not distant, it is here, beneath our feet and within every cell, hidden only by scale. It is the foundation upon which all else stands, the quantum heartbeat of the cosmos. At this deepest level, the question is no longer whether gravity is quantum, but what quantum itself means when space and time cease to exist. The answer may lie beyond mathematics, in a new language that merges geometry, probability, and information into one. Until we find that language, we stand at the shore of the Planck Sea, watching its foam shimmer at the edge of understanding. At the smallest scales, the very meaning of reality becomes uncertain. The Planck domain is not simply a limit of our technology, it is the place where the concepts of space and time themselves lose definition. Here, space-time is no longer a continuous fabric, but a flickering haze of possibilities. The smoothness of geometry gives way to a granular dance, where distances and durations are born, change, and vanish faster than the blink of existence. This is the quantum foam, the foundation of the universe that never rests. If one could shrink to that realm, there would be no sense of before or after, no here or there. Each tiny region would swell with energy, bending itself into miniature black holes that pop into being and evaporate almost instantly. These transient singularities are the punctuation marks in the language of space-time, forming and dissolving like thoughts. The average of their behavior becomes what we call the continuum, but the underlying story is chaos organized by probability. The laws of physics, as we know them, are the calm surface of a sea that hides infinite turbulence beneath. In this chaos, Einstein's equations no longer hold. They describe the curvature of space-time as though it were continuous, but at the Planck scale, there is no continuity to describe. The equations yield infinities, their terms collapsing under the weight of their own precision. They are perfect maps of a landscape that, at this depth, ceases to exist. It is as if the ink of general relativity fades, and a new script, written in the grammar of quantum mechanics, begins to emerge from the emptiness. Quantum theory, however, was not built for this terrain either. It assumes a background on which probabilities evolve, but in the Planck realm, there is no background. The canvas of space-time has dissolved. The wave function that describes all possibilities has no fixed arena to occupy. Even the idea of measurement falters. Because there is no stable observer to separate from what is being observed. The universe becomes self-referential, a network of interactions with no outside vantage point. At the heart of every black hole lies this mystery. When a massive star collapses under its own weight, its density grows until the curvature of space-time becomes infinite. According to general relativity, this singularity has no size and no volume. It is a point where the equations break. But infinity cannot exist in nature. Quantum mechanics tells us that uncertainty forbids such extremes. Somewhere near the center of a black hole, at scales close to the Planck length, gravity must become quantum and smooth out the singularity. The core of a black hole may therefore be not a point of infinite density, but a region where space-time itself folds into a quantum foam. This insight suggests that the beginning of the universe, the Big Bang itself, was not a singular explosion from nothing, but a quantum transition from one state of geometry to another. The early universe may have emerged from a Planck scale fluctuation, a bubble of space-time expanding from the foam. If true, then the laws of physics we observe today are the large-scale averages of microscopic, probabilistic rules that govern that first instant. The universe as we know it is the smoothed memory of its own quantum birth. The Planck realm therefore acts as a bridge between the visible and the hidden, the finite and the infinite. It is where the smooth tapestry of general relativity meets the granular weave of quantum mechanics. In this merging, time and space cease to be absolutes. They become emergent, arising from the interplay of information and energy. What we call gravity is the large-scale echo of this interplay, the shape taken by countless quantum interactions acting together. Every attempt to cross this frontier, mathematically or conceptually, leads to the same conclusion. Something must replace both general relativity and standard quantum theory. We need a new synthesis, a framework that treats space-time and quantum fields not as separate entities, but as aspects of one deeper reality. This is the quest for quantum gravity, a theory that can describe the foam and the stars with the same language. At the Planck scale, we encounter the raw engine of the cosmos. It is the boundary between being and becoming, between geometry and probability. The physics of this scale will not only explain how gravity becomes quantum, but also why the universe exists as it does. Smooth on the large, restless on the small, and governed everywhere by the balance between order and uncertainty. To seek the laws of the Planck realm is to seek the ultimate blueprint of existence. It is a pursuit that unites mathematicians, astronomers, and philosophers, for it touches on every question that science and reason have ever asked. What is reality? What is time? And can we ever know the world beneath its surface? From this smallest of scales, the next chapter of understanding begins. The search for a unified theory that reveals how space-time itself might be quantized, looped, or woven into the vast geometry of the universe. The Planck scale is the horizon of comprehension, the line where Einstein's geometry fades into quantum turbulence. Yet, to cross that line is to chase the most profound dream in physics, a single theory that unites the vast and the small, the curved and the uncertain. It is called the search for quantum gravity, and it stands as the final bridge between two visions of reality that have long refused to meet. For more than a century, gravity has remained the lone rebel among the forces of nature. Electromagnetism, the weak, and the strong interactions all obey quantum rules, their behaviors described by the delicate mathematics of quantum field theory. But gravity lives in another world, one of geometry and curvature, of smooth continua and absolute causality. Each theory works perfectly on its own, but when they meet, they tear each other apart. To find quantum gravity is to heal that rupture, to uncover the deeper law that makes both possible. Loop quantum gravity is one of the boldest attempts. It begins with the idea that space itself must be quantized, not continuous. The geometry of the universe, according to this theory, is built from discrete loops of gravitational field, tiny circuits of information that connect and weave into a network called a spin foam. Each loop represents the smallest possible quantum of area, each node the smallest quantum of volume. Together, they form a tapestry that vibrates and evolves, giving rise to the smooth spacetime of Einstein when viewed from afar. In this picture, gravity is not a force transmitted through space, but the dynamic behavior of space itself. The curvature that guides planets and bends light arises from the collective motion of these loops. Space and time are emergent, not fundamental. They are the large-scale shadows of a deeper, quantized geometry. Even the Big Bang in this view was not a singular beginning, but a bounce, a transition from a previous contracting phase of the universe. The infinite densities predicted by general relativity are replaced by a finite quantum structure that prevents collapse. String theory takes another path. It begins not with geometry, but with vibration. Instead of treating particles as points, it describes them as tiny one-dimensional strings whose different vibrational modes produce all known particles and forces. In this framework, gravity appears automatically, arising from one specific vibration, a massless spin-2 mode that behaves exactly like a graviton. The elegance of this result cannot be overstated. Gravity emerges as a natural consequence of the theory, rather than something added by hand. But strings demand a strange price. The mathematics only works if the universe has more dimensions than we can see. 10, or in some extensions, 11. The extra dimensions are thought to be compactified, curled up so tightly at the Planck scale that they remain invisible to us. Their hidden shapes determine the properties of the particles we observe, much like the shape of a violin determines its tone. If string theory is correct, then the diversity of matter and energy is the echo of geometry far smaller than atoms. Both loop quantum gravity and string theory seek the same destination, a quantum description of spacetime, but they approach it from opposite directions. One begins with Einstein's geometry and quantizes it directly. The other starts with quantum objects and lets geometry emerge from their behavior. Each captures part of the truth, and neither yet offers the whole. The universe may well be a combination of both ideas, or something beyond them entirely. Beyond these two giants lies a landscape of other possibilities. Causal set theory imagines space-time as a discrete set of events linked by cause and effect, with the geometry of the universe emerging from the order of those connections. Asymptotic safety proposes that gravity can be quantized if one treats spacetime as a scale-dependent entity, its properties changing smoothly from the quantum to the classical. Others explore the idea of emergent gravity, in which spacetime and gravity arise not from particles or fields at all, but from the thermodynamics of information, a statistical effect of microscopic degrees of freedom we have yet to uncover. These approaches share a single intuition that gravity's true nature is hidden beneath the smooth continuum, in a realm where space, time, and information intertwine. The goal is not only to write new equations, but to rewrite the language of reality itself. Quantum gravity is not merely a theory of force, it is a theory of existence. The difficulty is that every test lies far beyond the reach of our technology. The Planck length is smaller than anything we can probe, the Planck energy higher than anything we can achieve. We cannot build an accelerator powerful enough to reach that scale, nor a telescope sharp enough to resolve it. The evidence we seek must therefore come indirectly from the subtle fingerprints left by quantum gravity on the large-scale universe, in the echoes of black holes, in the ripples of space-time, in the entanglement of particles across vast distances. In the silence of these limits, the search becomes philosophical as much as physical. It asks whether space and time are fundamental or emergent, whether reality is made of things or of relationships. Perhaps gravity is not a force to be quantized, but a phenomenon to be understood statistically, like temperature or pressure. If that is true, then the path to quantum gravity lies not through particles, but through information. through the counting of microscopic states that give rise to the macroscopic curvature of the cosmos. Somewhere between the discrete loops of quantum geometry and the vibrating strings of higher dimensions, the true nature of gravity waits. It may not reveal itself as a new particle or equation, but as a realization that the universe itself is a quantum object, that its geometry is a form of entanglement, and that gravity is the expression of information flowing through that entanglement. The search for quantum gravity is therefore not just the next step in physics. It is the continuation of a story that began when we first noticed the pull of the Earth and wondered what held the stars in the sky. It is a search for the unity of all things: matter and energy, space and time, law and chance. The next clue, perhaps the most profound of all, comes from a startling idea: that gravity might not be fundamental at all, but a byproduct of something deeper: the thermodynamics of information itself. At the foundation of all these efforts lies a belief that nature is self-consistent, that the same principles shaping the quantum world must also govern the curvature of space-time. Loop quantum gravity begins with this conviction. It takes Einstein's equations not as continuous fields, but as quantized networks. Each link in the network carries a finite value of area. Each node encloses a tiny volume. The universe becomes a web of relationships, its geometry defined by the interconnection of these loops. When enough of them act together, the web behaves like a continuous fabric, giving rise to the spacetime of general relativity. In this picture, the smallest elements of reality are not particles, but bits of geometry. The surface of a black hole, for example, can be described as a mosaic of Planck-sized patches, each holding a quantum of area. The entropy of that surface, the measure of its hidden information, is proportional to its area rather than its volume. This strange fact, discovered by Jacob Bekenstein and Stephen Hawking, hinted that gravity might indeed be statistical, arising from the collective behavior of microscopic degrees of freedom. Loop quantum gravity gives that intuition a structure. It replaces the infinite singularities of general relativity with finite states, each one a possible configuration of the spin network that underlies space-time. String theory, by contrast, begins not with geometry, but with rhythm. In its equations, everything that exists is the vibration of a fundamental string. The frequency of vibration determines the nature of the particle, whether it is an electron, a photon, or a graviton. The interactions between strings correspond to the splitting and joining of these tiny filaments, and their harmonies generate the forces and matter of the universe. The strength of this idea lies in its unity. One object, many manifestations. But it comes with a cost: the need for extra dimensions and for a landscape of possible solutions so vast that predicting our universe among them remains a mystery. Despite their differences, both theories point toward a deeper symmetry. In both, the geometry of space is not continuous. It is made of discrete entities. In both, the fabric of reality is dynamic and relational, a process rather than a thing. And in both, the boundary between space-time and information becomes blurred. The holographic principle, emerging from the mathematics of string theory, takes this blur to its logical conclusion. Everything inside a volume of space can be described by information encoded on its boundary. The three-dimensional world may be a projection of data stored on a distant surface, much like a hologram. If this is true, then gravity itself might be the manifestation of that encoding. The curvature of space-time could correspond to the flow of information across the boundary of a system. When mass and energy distort space-time, they may simply be redistributing information within the holographic field. The equations of Einstein become equations of thermodynamics, relating energy, entropy, and temperature rather than distance and curvature. This idea bridges general relativity and quantum mechanics through the language of information, revealing that the geometry of the universe might be a macroscopic expression of microscopic entropy. In this emerging view, Space-time is not the stage of the cosmos, but its product. Gravity is not a fundamental interaction, but the large-scale behavior of quantum information seeking equilibrium. Just as heat arises from the random motion of atoms, gravity could arise from the statistical tendencies of unseen microstates. When we describe a planet orbiting a star, we might be describing not a force pulling at a mass, but an entropic flow restoring balance in the informational fabric of the universe. These ideas, though abstract, produce real predictions. They suggest that black holes should radiate energy because of quantum effects at their horizons, that their entropy should equal 1/4 of their surface area measured in Planck units, and that the information swallowed by them must somehow be preserved. The fact that Hawking radiation fits these expectations gives the hypothesis remarkable weight. Gravity, once seen as the most classical of forces, begins to look like the most quantum of all. Theories of quantum gravity thus converge on a single insight. Space, time, and gravity may be emergent phenomena arising from deeper layers of quantum information. The Planck scale, once thought to mark the end of physics, becomes its beginning. From that foundation, everything else, the expansion of the universe, the flow of time, the structure of galaxies, may unfold naturally. What remains is to find the experiment that can confirm it, to detect the faint fingerprints of quantum geometry imprinted on the cosmic canvas. For now, the search continues in the quiet hum of computers and the faint tremors of gravitational observatories. Each equation written, each signal captured, is a small step toward the same truth. The realization that gravity, the force that shapes stars and bends light, might not be a force at all, but the echo of something deeper. The statistical whisper of information becoming space. At the edge of mathematics, where symbols blur into meaning, the search for quantum gravity becomes something more than physics. It becomes an inquiry into what existence itself might be made of. Every path we follow seems to lead toward the same quiet realization. Space-time, gravity, and even the flow of time may not be fundamental at all. They may be emergent, like patterns forming on the surface of something deeper. In loop quantum gravity, the smallest grains of space do not live inside a pre-existing geometry. They are the geometry. When enough of these quanta connect, a continuous space-time appears, much as the smoothness of water arises from countless molecules moving in harmony. The flow of time itself is not an external clock, but the evolution of these interconnections. Time ticks because relationships change. The universe becomes a network that continually rewrites itself. In string theory, the story is told through vibration. Each string is a pulse of energy that extends through hidden dimensions, its resonance defining both matter and force. When these strings interact, they weave a higher dimensional tapestry, and the shape of that tapestry determines the geometry of the universe we perceive. Gravity is not added to this picture. It is inevitable. The spin-2 vibration of the string is the graviton, the quantum ripple of space-time curvature. In this vision, the universe sings its structure into being, every particle a note in an endless symphony of motion. The holographic principle pushes this vision further still. It tells us that everything within a region of space, every atom, every photon, every fluctuation of a field, can be described by information encoded on the region's boundary. The interior, in a sense, is just a projection. The universe, then, may be a vast hologram, its depth and motion illusions produced by the quantum information imprinted on its cosmic surface. In this holographic universe, gravity emerges naturally as the curvature of the projection itself, the shape of information made visible. Eric Verlinde took this idea and gave it new form. He proposed that gravity is not a fundamental force at all, but an entropic phenomenon, a statistical effect of information-seeking balance. When information is distributed unevenly, it creates gradients of entropy. Objects move along those gradients, just as heat flows from hot to cold. What we call gravitational attraction is, in this picture, the universe striving toward informational equilibrium. Space curves not because of mass alone, but because of the rearrangement of information within the quantum fabric. This hypothesis, while radical, explains some of the most puzzling mysteries in cosmology. The anomalous rotation of galaxies, for instance, which led to the concept of dark matter, may instead arise from the way information is stored in spacetime. The apparent need for invisible mass could be a sign that our understanding of gravity's emergent behavior is incomplete. If gravity truly stems from entropy, then its strength and range would vary subtly with scale, producing effects that mimic the presence of unseen matter. Such ideas shift our understanding of the universe from a mechanical system to an informational one. The cosmos becomes a processor of data, an endless computation unfolding across its own geometry. Black holes, instead of being cosmic abysses, become storage devices, their horizons encoding every bit of information that falls in. The second law of thermodynamics, that entropy never decreases, becomes the law of cosmic evolution itself, guiding the universe toward greater complexity and knowledge. If gravity is indeed emergent, then Einstein's equations are not fundamental laws, but statistical approximations. They describe how the macroscopic geometry behaves when countless quantum bits of information average together. In the same way that temperature describes the collective motion of molecules without revealing their individual paths, the curvature of spacetime describes the collective flow of information without revealing its microscopic structure. Einstein's insight remains true, but it may be a surface truth, a reflection of something deeper beneath. The search for quantum gravity, then, becomes a search for the rules by which information organizes itself into geometry. It is a quest to understand how bits become atoms, how entropy becomes attraction, how the statistics of unseen degrees of freedom give birth to the force that shapes the stars. It is a journey from matter to meaning. As we explore this frontier, experiments begin to catch up with imagination. Tabletop interferometers now measure the quantum motion of microscopic masses suspended in vacuum. Quantum computers simulate the entanglement patterns that might underlie spacetime. Astronomers map gravitational waves and trace their ripples back to the first instance of creation. Each observation, each data point, whispers of the same truth: that geometry is not fixed, but fluid, that gravity is not a command, but a conversation. To find quantum gravity is to find the code of the universe, whether it is written in loops or strings, in holographic surfaces or entangled qubits. That code will tell us how the large arises from the small, how continuity emerges from discreteness, and how the universe computes its own existence. The next step in this search will take us beyond theory and into the realm of pure emergence, where gravity reveals itself not as a particle or a field, but as the inevitable result of information itself. Gravity has always seemed fundamental, a force that shapes everything, yet asks for nothing. But what if this force is not fundamental at all? What if it is the shadow of something deeper, the surface echo of invisible processes playing out in the unseen machinery of the universe? To call gravity emergent is to challenge everything we think we know about reality. It is to suggest that space-time, curvature, and attraction are not built into the foundations of existence, but arise naturally from the collective behavior of something else, something quantum, statistical, and profoundly informational. Eric Verlinde proposed such an idea, describing gravity not as a fundamental force, but as an entropic one, a consequence of the way information arranges itself. In his vision, the universe is an information field, and gravity emerges when that information is out of balance. The motion of planets and the curvature of space-time become not the results of force and mass, but of entropy and equilibrium. Matter moves the way it does because the universe is always seeking to restore informational harmony. When something disrupts that balance, the result looks to us like gravity. This view turns Einstein's equations into a kind of thermodynamic identity. They no longer describe a fundamental interaction, but the macroscopic behavior of countless microscopic degrees of freedom, the unseen bits of quantum information that make up space-time itself. Just as temperature arises from the collective motion of molecules, gravity arises from the collective statistics of quantum information. When we warm our hands by a fire, we are not feeling individual particles, but the emergent phenomenon of heat. Likewise, when the Earth falls toward the Sun, it may be following not a pull, but an entropic path, the most probable configuration for the information that defines space-time. To see how this works, imagine a holographic surface surrounding any region of space. According to the holographic principle, the amount of information that can be stored within that region is proportional to the area of its boundary, not its volume. This means that what happens inside space can be encoded on its edges. Verlinder's insight was that gravity could arise as a natural consequence of that encoding. The motion of matter changes the information content of space, and space responds by adjusting its geometry. The curvature we perceive as gravitational attraction is, in this sense, a bookkeeping effect, the universe rebalancing its information. In this model, space-time itself is emergent. It is not a fixed arena, but a statistical manifestation of underlying microstates. Where information is dense, space-time curves. Where it is sparse, it flattens. The equations of general relativity emerge naturally from this thermodynamic picture, just as the laws of fluid dynamics emerge from the collective motion of molecules. Gravity becomes the most elegant illusion in nature, not a force acting across distance, but the smooth result of quantum information aligning itself across the cosmos. This view also sheds light on the strange relationship between gravity, entropy, and black holes. When matter collapses into a black hole, its information is not lost but stored on the horizon, the holographic surface that separates the inside from the outside. The entropy of the black hole is proportional to its area because the horizon encodes every bit of information that once existed within. Hawking radiation, the faint glow that leaks from the edge of a black hole, is the process by which that information returns to the universe, one quantum at a time. Even the most violent singularities obey the quiet laws of thermodynamics. The elegance of this framework is that it links gravity, quantum mechanics, and thermodynamics into a single narrative. It explains why Einstein's equations mirror the equations of heat and energy flow, and why black holes have temperature and entropy. It transforms our understanding of space from a geometric entity into an informational one. The universe, in this view, is not a collection of things in space. It is the information that defines space. If this is true, then every particle, every photon, every fluctuation of vacuum energy is not an independent object, but a pattern in the informational fabric. Reality becomes a self-organizing system, where what we call forces and fields are simply emergent patterns of balance. Gravity, the most ancient mystery of all, turns out to be a property of knowledge itself, the way information bends under its own weight. This idea does not diminish Einstein's insight, it deepens it. General relativity remains the correct description of gravity on large scales, just as thermodynamics correctly describes the behavior of gases without referencing individual molecules. But beneath it lies the statistical dance of quantum states, the hidden architecture that gives rise to space-time. The beauty of relativity was that it united space and time into a single fabric. The beauty of emergent gravity is that it reveals that fabric to be woven from information. The implications are vast. If space-time is emergent, then it can fluctuate, tear, and reconnect not through classical motion, but through changes in information. Wormholes, black holes, and cosmic expansion all become informational phenomena. The entire evolution of the universe can be seen as a computation, an unfolding of information through the quantum network that underlies reality. To understand gravity, then, is to understand how that computation works. The next step in this story takes us to the most extreme laboratories nature provides, black holes. These cosmic engines of entropy and information stand at the intersection of quantum theory and general relativity. They radiate, evaporate, and yet somehow preserve the information of everything they consume. Within their horizons may lie the clues that reveal whether gravity truly is emergent, and whether the fabric of spacetime is woven not from matter or energy, but from the pure logic of quantum information itself. In the quiet mathematics of the cosmos, gravity begins to resemble a form of memory. It is as though the universe keeps track of every interaction, every bit of energy and matter, by adjusting its own geometry. When we move through space, we are not merely traveling across emptiness. We are rewriting the informational structure that defines where and when we are. The curvature we call gravity is this rewriting made visible. Every orbit, every fall, every wave of light bending through the dark is a conversation between information and space. The link between gravity and information becomes clearest at the edges of black holes. When a star collapses under its own gravity, its mass and energy become trapped behind an event horizon, a boundary from which nothing, not even light, can escape. Classical physics says the story ends there. The star's matter is gone forever. But quantum mechanics refuses to stay silent. It insists that information cannot be destroyed. If black holes swallow everything, where does that information go? Stephen Hawking's discovery of black hole radiation deepened this paradox. His equations showed that black holes emit faint thermal radiation due to quantum effects near the horizon. Over eons, this radiation causes them to evaporate, fading slowly into nothingness. Yet thermal radiation carries no specific information about what fell in. If the black hole truly disappears, the information that once defined its contents would be lost, a direct violation of quantum law. This is the information paradox, one of the deepest puzzles in theoretical physics. In the framework of emergent gravity, the paradox begins to resolve itself. The event horizon is not a simple surface, but an informational boundary. The data describing everything that falls in is encoded on this boundary, stored as microscopic degrees of freedom, qubits of spacetime itself. The radiation that escapes is not random, but carries subtle correlations, slowly releasing that information back into the universe. The process is unimaginably complex, but it ensures that nothing is ever truly lost. The holographic nature of spacetime preserves the universe's perfect accounting. This perspective transforms our image of a black hole. No longer a featureless void, it becomes the most intricate structure imaginable. A cosmic archive storing the history of everything it consumes. Its surface is a living tapestry of quantum information, constantly fluctuating and evolving. The entropy of the black hole measures how many microscopic configurations correspond to the same macroscopic appearance. It is a count of all the possible ways the horizon can encode its data while maintaining the same overall geometry. When matter approaches the horizon, its information does not vanish. It becomes entangled with the degrees of freedom of spacetime itself. The gravitational pull we feel near such an object is the manifestation of that entanglement. The black hole's geometry adjusts as new information is added, redistributing entropy to maintain equilibrium. Gravity, once again, reveals itself as a thermodynamic response, the system's drive to balance the flow of information. This view also explains why the equations of general relativity mirror the laws of thermodynamics. The Einstein field equations can be derived from the principle that entropy must always increase along any causal horizon. In other words, the geometry of spacetime arranges itself to ensure that the second law of thermodynamics is never violated. Temperature, energy, and curvature are no longer separate concepts, but different expressions of the same underlying logic. If the universe follows these rules, then even the expansion of space may be a thermodynamic process. The cosmic horizon, the edge beyond which we cannot see, could be another informational boundary, radiating energy as it grows. The acceleration of that expansion, attributed to dark energy, might arise naturally from the entropic behavior of the horizon itself. In this sense, the entire cosmos could be a single thermodynamic system, evolving toward equilibrium on a scale too vast for human intuition. To describe reality this way is to see physics as the study of information in motion. Mass, energy, and geometry become emergent properties of that motion. The laws of the universe reduce to the laws of information flow, conservation, transformation, and entropy. The beauty of this vision is that it reconciles the classical and quantum worlds without forcing them to fit awkwardly together. Gravity is not an exception to quantization. It is what quantization looks like when viewed from afar. In the language of quantum mechanics, information is stored in entanglement, the invisible correlations that link particles even when they are light years apart. The holographic principle suggests that spacetime itself is woven from these entanglements. Each connection between quantum systems becomes a thread in the fabric of space. Where entanglement is strong, spacetime is connected. Where it weakens, space stretches or even tears. Gravity, then, may be the curvature that emerges from the pattern of these connections. If that is true, we no longer need to ask why gravity is quantum. Gravity is the quantum. It is the manifestation of entanglement on a cosmic scale. The motion of planets, the bending of light, the collapse of stars are all expressions of quantum information shaping the geometry of existence. In this view, to understand gravity is to understand how information becomes reality. The story of emergent gravity brings us to a profound realization. We are part of the information field. The atoms in our bodies, the photons that reach our eyes, the neurons that form our thoughts, all are fluctuations in the same informational web that gives rise to space-time itself. The universe does not exist in space. The universe is space, continuously created and sustained by the flow of information. Gravity is the heartbeat of that flow. As we continue to explore these ideas, we are drawn inevitably toward the ultimate test, the black hole, where gravity and quantum mechanics meet face to face. In those extreme environments, we may finally glimpse the hidden machinery of emergent gravity, the place where information, entropy, and space-time converge into one. For within a black hole's darkness lies the brightest clue of all, a doorway to the quantum structure of reality. At the edge of a black hole, physics and philosophy merge. The event horizon is a boundary unlike any other, both physical and informational. It separates what can be known from what can never be seen. To an outside observer, time slows near this surface. Light stretches and fades, and all signals drift towards silence. Yet beneath that silence, the most intricate processes in the universe unfold, the quantum encoding of reality itself. Hawking's discovery that black holes radiate changed everything. It proved that even the most extreme gravitational objects obey the laws of quantum mechanics. A black hole emits faint radiation as virtual particle pairs form near the horizon. One particle escapes as light, while the other falls inward, effectively stealing a sliver of the black hole's mass. Over unimaginable spans of time, the black hole evaporates, dissolving into a mist of photons and particles. But what happens to the information it once contained? If the radiation is purely thermal, then it carries no record of what created it. The black hole would evaporate into featureless heat, erasing the details of every planet, star, or atom that ever fell within. This is the essence of the information paradox, the collision between quantum mechanics, which demands that information is conserved, and general relativity, which allows it to vanish behind an event horizon. The universe cannot tolerate both. In the framework of emergent gravity, this paradox begins to resolve itself. The information that falls into a black hole does not disappear. It becomes encoded in the microscopic degrees of freedom of the horizon. The surface of the black hole functions like a cosmic memory chip, recording everything that crosses it. As the black hole radiates, this information gradually leaks back into the universe in subtle correlations within the emitted particles. The process is so delicate that it appears random, but buried within the radiation is the complete record of everything the black hole has consumed. Information is never lost, it merely changes form. This understanding connects the physics of black holes to the thermodynamics of ordinary systems. Entropy, temperature, and information, concepts born in the study of heat engines and gases, turn out to describe the behavior of spacetime itself. The entropy of a black hole, as Bekenstein and Hawking showed, is proportional to the area of its horizon in Planck units. Each Planck-sized patch represents one bit of information, one quantum of the universe's hidden code. The more massive the black hole, the greater its informational capacity. In a sense, the horizon acts as the ultimate compression algorithm. It stores the maximum possible amount of data that can fit within a given region of space, a principle known as the holographic bound. No physical system can contain more information than a black hole of the same size. This realization does not merely apply to black holes, it applies to the entire universe. Every region of space has an upper limit to how much information it can contain, and this limit is set not by volume, but by surface area. Space, it seems, measures itself in bits. This holographic nature suggests that the universe we inhabit might be the projection of a deeper, two-dimensional reality. Just as a hologram stores a three-dimensional image on a flat surface, the cosmos may store its three-dimensional geometry on a vast cosmic boundary. Our reality would then be the emergent image of this underlying information, light and matter woven from quantum codes inscribed on the edges of spacetime. The curvature we call gravity would be the pattern by which those codes are interpreted. In this vision, a black hole becomes not a tear in space, but a window into the informational foundation of the universe. Its radiation, rather than being a mystery, is a conversation. Information leaving one form to reappear in another. When we decode that conversation, we will not only solve the information paradox, but also uncover the rules by which spacetime itself is written. Hawking's radiation is not a threat to quantum mechanics. It is its proof, showing that even gravity must obey the conservation of information. The implications stretch far beyond black holes. If spacetime and gravity emerge from information, then every physical law is an emergent law. Energy conservation, quantum entanglement. Even the arrow of time could be statistical effects of information flow. The universe would not be a static structure of matter and geometry, but a dynamic computation. A self-sustaining system that evolves by processing its own data. Every star that shines, every particle that collides, every thought that arises is part of that computation. Gravity is the geometry that this computation naturally assumes. When we look into the night sky, we are not seeing distant objects frozen in space. We are witnessing information unfolding, light tracing the structure of the universe's code across billions of years. The galaxies we see are ripples in that code, frozen snapshots of an ongoing calculation. The cosmos is not a creation, but a continual act of computation, with gravity as its syntax and spacetime as its grammar. The theory of emergent gravity leads us to an unsettling but beautiful conclusion. The universe may not be built from matter or energy, but from information. Matter and energy are how information manifests itself. Spacetime is how it connects. Gravity is the rule that ensures coherence in the great computation, keeping the code consistent from one moment to the next. If that is true, then we ourselves are not separate from it. Every neuron, every molecule, every heartbeat is an instance of the same code, written in the same universal language. The human mind is one of the ways the universe processes its own information, one of the ways the cosmos becomes aware of itself. Gravity, in this light, is the conversation between being and knowing, the weight of information pressing against the boundaries of reality. The next step in this journey will take us deeper into that conversation, into the realm of black holes where quantum entanglement, information, and geometry intertwine. For it is there, at the edge of nothingness, that the universe reveals how profoundly quantum its gravity truly is. Black holes are the most mysterious objects in the universe, simple in appearance, yet deeper than any ocean of thought. They are born when gravity overwhelms everything else, when the pull of matter folds space upon itself until not even light can escape. To classical physics, a black hole is finality itself, a region from which no information can return. But to quantum physics, it is something far stranger, a laboratory for the ultimate secrets of reality, a bridge between the smooth geometry of Einstein and the restless fluctuations of the quantum world. Imagine a star many times more massive than the Sun collapsing under its own gravity. As it implodes, the density becomes so great that space-time curves without limit. At its center lies a singularity, a place where all known laws fail, where curvature becomes infinite and meaning itself dissolves. Surrounding it is the event horizon, the invisible boundary beyond which nothing can escape. From a distance, the black hole appears perfectly black, its details hidden behind that horizon. It seems to erase the difference between things, reducing all matter to uniform darkness. Yet the story, as quantum mechanics insists, is never that simple. In the 1970s, Stephen Hawking asked what would happen if we applied quantum theory to the empty space around the horizon. His answer changed physics forever. Quantum fields are never truly empty. They flicker with virtual particles, pairs that continually appear and annihilate, borrowing energy from the vacuum for a moment shorter than a Planck time. Near an event horizon, these pairs can be torn apart, one particle falling in, the other escaping to infinity. To a distant observer, it looks as though the black hole is emitting radiation. Over time, it loses mass, shrinking and growing hotter until it eventually evaporates completely. This faint emission, now known as Hawking radiation, revealed a hidden truth. Black holes are not eternal prisons, but thermodynamic objects with temperature and entropy. They obey the same laws that govern steam engines and melting ice. Their temperature is inversely proportional to their mass, and their entropy, a measure of the information hidden behind the horizon, is proportional to the area of that horizon, not its volume. For every bit of area equal to the Planck length squared, the black hole contains 1 unit of information. The larger the black hole, the more data it holds. Here lies a breathtaking insight. Gravity and thermodynamics are 2 sides of the same coin. The curvature of space-time, the motion of planets, and the heat of a black hole all stem from the same underlying logic: the tendency of information to arrange itself into equilibrium. The laws of Einstein can even be derived from the laws of entropy. This unity suggests that gravity itself might be a macroscopic phenomenon, the large-scale expression of quantum information moving toward balance. But Hawking's discovery also created a paradox. If black holes evaporate through thermal radiation, what happens to the information of the matter they consume? Quantum mechanics demands that information can never be destroyed. Every state of a system must evolve into another state containing the same information, even if rearranged. If a black hole truly disappears into featureless radiation, then the information it contained is lost forever, a violation of the fundamental laws of quantum theory. For decades, this contradiction haunted physics. Jacob Bekenstein had already shown that black holes have entropy, and that this entropy must correspond to hidden microstates, unseen ways that the black hole's interior can arrange itself while looking the same from outside. The question was, what are those microstates, and how can they release their information? The holographic principle offered a possible answer. It proposed that everything inside a region of space can be described by information encoded on its boundary. For a black hole, that boundary is the event horizon. The information about everything that falls in is not lost. It is written on the horizon's surface, stored in quantum bits smaller than imagination. If this principle is true, then the universe itself may be holographic. What we experience as 3-dimensional space could be a projection of quantum information encoded on a distant cosmic boundary. Space would not contain information. It would be information. The geometry of space-time, the bending that we interpret as gravity, would emerge from the entanglement structure of these quantum bits. Gravity would not be a fundamental force, but the visible shape of invisible connections. In recent decades, this idea has gained astonishing support from theoretical models. The correspondence known as ADS-CFT, a bridge between a theory of gravity in a curved space-time and a quantum field theory without gravity living on its boundary, demonstrates that a gravitational world and a purely quantum world can be mathematically equivalent. In that duality, every point of space corresponds to a network of entangled quantum states. The depth of the space-time is the strength of those entanglements. In this view, space-time itself is woven from quantum links, and a black hole is the densest knot in that weave. The entanglement that builds space-time also explains the mystery of Hawking radiation. The escaping particles are not independent of the black hole. They are entangled with what remains inside. As evaporation continues, these correlations carry away the hidden information, encoded in subtle quantum patterns. To an observer with limited knowledge, the radiation looks random, but in principle, it contains everything that fell into the hole. If one could measure it with perfect precision, the universe would appear to have kept its perfect accounting after all. The concept that space-time emerges from entanglement is more than a poetic metaphor. It has become a working hypothesis for the quantum structure of reality. When entanglement between two regions is strong, space between them is short. When entanglement weakens, space stretches. If entanglement disappears completely, space tears apart. This is the meaning behind the phrase entanglement creates geometry. In the black hole, where entanglement is maximal, space folds so tightly that the interior becomes disconnected from the outside. The horizon is not a wall, but a transition in connectivity, a change in the pattern of quantum relationships that define space itself. If we could peer beneath the event horizon, we would not find a singularity in the classical sense. Instead, we would find a tangle of quantum connections, a storm of entanglement so intense that the notion of location breaks down. Some physicists suspect that these connections may even manifest as wormholes, tunnels of space-time linking distant regions. The conjecture known as ER equals EPR proposes that every pair of entangled particles is connected by a microscopic wormhole, and that the geometry of space-time on the largest scales may simply be the sum of all these quantum bridges. If true, then the universe is not a collection of separated objects, but a single, woven whole, a network of relationships extending through time and space. Black holes, then, are not cosmic dead ends, but laboratories for the quantum origin of gravity. They show us that information is never destroyed, that geometry and entropy are intertwined, and that space-time itself may be a quantum network of connections. They remind us that gravity is not merely the curvature of space, but the curvature of knowledge, the way information bends under its own complexity. The implications reach beyond physics. If reality is built from information, then every process, from the birth of stars to the firing of neurons, is part of a universal computation. The universe evolves not because of forces acting in space, but because information transforms according to consistent rules. The past, present, and future are not fixed moments along a line, but successive states of a cosmic calculation. In this computation, black holes are both processors and memory, places where the code grows most dense, where the universe reflects upon itself. As our understanding deepens, the boundary between matter and information begins to vanish. What we call energy is the ability to change information. What we call entropy is the number of possible ways that information can be arranged. What we call gravity is the tendency of information to organize itself into coherent geometry. The quantum clues from black holes tell us that everything we experience, light, time, motion, and form arises from these informational principles. In this new perspective, Einstein's vision of gravity and quantum theory's vision of probability merge into one story. The geometry of space-time and the logic of entanglement are two expressions of the same reality. The universe is not a static structure of objects, but a living web of relationships, continuously calculating its own evolution. Black holes, once thought to be cosmic destroyers, turn out to be teachers, showing us how nature guards its information and how gravity reveals its quantum heart. Perhaps one day, when we fully understand these lessons, we will see that gravity is not a force at all, but the shadow of entanglement, the visible trace of invisible correlations binding every particle, every photon, and every star. Space itself may be the ultimate illusion, the grand tapestry woven by quantum threads of connection. And in those threads, shimmering at the edge of black holes and across the vastness of the cosmos, we may glimpse the true architecture of reality. At the deepest level, the universe is not made of particles or fields, but of relationships. Entanglement is the invisible thread that connects those relationships, the quantum link that binds distant events into a single whole. It defies classical logic, allowing two particles to share a single state no matter how far apart they drift. What happens to one instantly affects the other, as if distance itself were an illusion. For centuries, this phenomenon was treated as a curiosity, an oddity at the heart of quantum mechanics. But in recent decades, it has revealed itself as the very foundation of reality, the loom upon which space-time itself is woven. In the 1930s, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper questioning the completeness of quantum mechanics. They described a thought experiment where two particles become entangled and then separated by vast distances. Measuring one instantly reveals the state of the other. To Einstein, this seemed impossible. He called it spooky action at a distance. He believed that quantum mechanics must be incomplete, that hidden variables would one day restore the separability of reality. But experiments over the next 50 years proved otherwise. Entanglement was real, and it violated every expectation of classical intuition. This same trio of names, Einstein, Podolsky, and Rosen, would return decades later in a radically new context. Physicists studying black holes began to suspect that the geometry of space-time itself might be linked to entanglement. If particles can remain connected across light years without any signal passing between them, then perhaps the universe itself is a network of such connections. In this framework, distance is not fundamental. It is defined by how much two systems are entangled. Where entanglement is strong, space is close. Where it is weak, space stretches apart. The very structure of geometry may emerge from the pattern of quantum correlations. Juan Maldacena and Leonard Susskind gave this idea a name: ER equals EPR, uniting the ancient paradox of entanglement with the geometry of wormholes. The ER stands for Einstein-Rosen, referring to the theoretical bridges in space-time that connect two regions through a tunnel. The EPR refers to the entanglement paradox itself. The conjecture is audacious in its simplicity. Every entangled pair of particles is connected by a quantum wormhole. The wormhole may be too small and unstable to observe, but it encodes the same correlation that entanglement describes. Entanglement and geometry, in this view, are two expressions of the same physical reality. If ER equals EPR is correct, then spacetime is not a static background, but an emergent network, a cosmic web of wormholes linking every part of the universe. Every atom, every photon, every quantum field is stitched together by these connections. The curvature of space becomes a reflection of how densely entangled those connections are. Gravity, rather than being a force transmitted through space, becomes a measure of how the network bends and warps when entanglement changes. The smooth fabric of spacetime is the collective behavior of countless quantum threads intertwining and vibrating across reality. The implications are staggering. It means that space has no independent existence apart from the quantum states that inhabit it. If one could somehow turn off all entanglement, the universe would not just become empty, it would cease to exist. There would be no distance, no motion, no geometry. Space is not where things are. It is what arises when things are connected. The universe, therefore, is less like a stage and more like a living network of relationships, continuously updating itself through quantum communication. This picture also reshapes our understanding of time. In quantum theory, entanglement evolves according to the Schrödinger equation, a smooth and deterministic process. But the direction of time, the arrow that distinguishes past from future, emerges from the growth of entanglement. As systems interact, they become more entangled with their surroundings, and information spreads outward irreversibly. Entropy increases because entanglement increases. Time flows because the web of quantum correlations becomes ever more complex. In this way, the arrow of time is written into the structure of spacetime itself. When we consider the universe in this light, everything becomes relational. Position, momentum, energy, and even causality depend on how systems are connected within the global network of entanglement. Black holes, which were once seen as boundaries of ignorance, become the most entangled objects of all, regions where information is compressed to its ultimate density. Their event horizons are the interfaces where quantum information reorganizes itself into new geometric forms. The smoothness of their curvature is the visible manifestation of perfect entanglement among the underlying quantum bits. In the holographic framework, this insight gains mathematical precision. The amount of entanglement between two regions in the boundary quantum field theory determines the geometry of the spacetime in the higher dimensional bulk. Entanglement is not just correlated with geometry, it is geometry. The curvature of space, the shape of gravitational fields, and even the existence of horizons can all be derived from patterns of quantum correlation. In this sense, Einstein's general relativity becomes an emergent description of how quantum information organizes itself at large scales. What is most extraordinary is how this vision unites opposites. The smooth, continuous world of relativity arises from the discrete, probabilistic world of quantum mechanics. Deterministic geometry emerges from stochastic entanglement. The apparent solidity of spacetime conceals a fluid, dynamic network of quantum relationships. Einstein's curvature and Schrödinger's wave function, once seen as incompatible, are revealed to be aspects of the same underlying structure, one describing the visible surface, the other the invisible connections beneath. If entanglement is indeed the substance of spacetime, then understanding it is the key to everything. It would explain not only gravity, but also cosmology, dark energy, and perhaps even the origin of the universe itself. The Big Bang in this picture might have been not the creation of matter from nothing, but the sudden ignition of universal entanglement, the moment when separate quantum systems became one. The expansion of space would then be the gradual weakening of entanglement across the cosmic network, stretching the threads that bind galaxies together. This vision turns every question about physics into a question about information. Why does matter have mass? Because mass is a measure of how information resists change. Why does gravity curve spacetime? Because the structure of entanglement shifts when information moves. Why is the speed of light constant? Because it is the rate at which information propagates through the network. The laws of physics become the grammar of information flow, the syntax by which reality computes itself. In the laboratory, physicists are beginning to test these ideas. Quantum computers simulate tiny universes in which spacetime emerges from patterns of entanglement between qubits. Experiments with ultra-cold atoms and photonic lattices mimic miniature holographic systems, showing how geometry can arise from quantum correlations. Even gravitational wave detectors, sensitive to the faintest tremors in spacetime, might one day reveal the fingerprints of quantum entanglement encoded in cosmic ripples. The boundary between theory and observation is narrowing, and the idea that space is built from entanglement moves steadily from speculation toward fact. To imagine the cosmos this way is to see it as a living fabric of connection. Every particle is a node in a vast quantum web. Every force is a pattern in that web. Every act of measurement is a ripple that rearranges its structure. The universe is not a machine made of parts, but a conversation made of relationships. When we look across the night sky, the starlight we see is not just photons traveling through space. It is information flowing through the threads that make space real. In this light, gravity ceases to be a separate force. It becomes the statistical behavior of entanglement on a cosmic scale, the way the quantum network curves to maintain its coherence. The planets orbit not because they are pulled by invisible hands, but because the geometry of their entanglement with the rest of the universe dictates that motion. Spacetime, the stage upon which all things occur, is not fundamental. It is the pattern formed by the collective harmony of quantum links. And so, entanglement is not merely a feature of quantum mechanics. It is the thread from which reality is woven. Space, time, energy, and gravity are its emergent properties, the visible surface of an invisible order. The cosmos itself is a single, unified quantum state, endlessly evolving, forever connected. When we trace the threads of entanglement, we are not merely studying the universe. We are uncovering the very logic of existence, the code by which reality writes itself. For centuries, gravity has been the most patient of mysteries. We have watched it sculpt galaxies, bend starlight, and govern the dance of planets, yet we have never touched its quantum heart. Every other force, electromagnetic, weak, and strong, has revealed its quantum face through the exchange of particles, but gravity remains silent, whispering only through the slow curvature of space-time. The challenge of our age is to catch that whisper, to see whether gravity itself is a quantum phenomenon, woven from the same entanglement that defines all else. Until recently, the idea of probing quantum gravity in the laboratory seemed impossible. The Planck scale, where gravity becomes quantum, is so far beyond our reach that it makes direct detection appear hopeless. To see a single graviton, the hypothetical quantum of gravity, would require a detector so large and sensitive that it would collapse into a black hole under its own weight. The energy required to probe such scales exceeds the total energy available in any experiment ever conceived. Yet physicists, driven by imagination and precision, have begun to find new paths, subtle, ingenious ways to test whether gravity can entangle, interfere, or superpose like any other quantum field. The first clues may come from the tiniest of systems, not the grandest. In recent years, laboratories have begun to place small masses, spheres of gold or silica no larger than a speck of dust, into delicate quantum superpositions. Suspended in vacuum and cooled to near absolute zero, these objects hover between two positions at once, their wave functions overlapping like ripples on a still pond. If gravity is classical, the two positions should remain independent. But if gravity is quantum, then the gravitational field of one position should entangle with that of the other, creating interference patterns that can, in principle, be measured. Two independent proposals, often called the BMV experiments after their creators, suggest that by bringing two such superposed masses close together, we could watch them become entangled solely through their mutual gravitational attraction. If this entanglement occurs, it would mean that gravity cannot remain purely classical. It must itself be a quantum mediator. The effect would be faint beyond imagination, yet not beyond possibility. With technology improving by orders of magnitude each decade, we stand at the threshold of being able to detect gravity's quantum handshake for the first time. At the same time, the great observatories of the cosmos are listening. Instruments like LIGO and Virgo have already detected the ripples of space-time from colliding black holes and neutron stars. These gravitational waves are classical in origin, but hidden within their patterns could be subtle traces of quantum behavior. The fluctuations in their amplitude, the fine structure of their frequency, might carry hints of quantum discreteness, echoes of spacetime's atomic grain. Future missions like LISA, a constellation of satellites stretched across millions of kilometers, will open an even more sensitive ear to the sky. Each vibration it hears could carry whispers from the Planck frontier. Other experiments are turning inward, toward the vacuum itself. The quantum vacuum is not empty. It is a seething ocean of virtual particles that flicker in and out of existence. Gravity couples to this energy, but how it does so remains a mystery. The cosmological constant problem, the mismatch between the predicted and observed vacuum energy, is perhaps the clearest sign that we do not yet understand gravity's quantum behavior. By studying the minute deviations in the expansion of the universe, and by mapping the cosmic microwave background with ever greater precision, cosmologists hope to uncover how gravity responds to the quantum fluctuations that fill all of space. Another frontier lies in the search for gravitational decoherence. In quantum theory, systems remain coherent, maintaining their superpositions, until they interact with an environment that effectively measures them. Gravity might act as such an environment, collapsing quantum states not through observation, but through curvature. If so, then the scale at which superposition fails could reveal the bridge between quantum mechanics and relativity. Experiments now underway with levitated nanoparticles, atomic interferometers, and superconducting circuits are testing whether gravity alone can destroy or preserve quantum coherence. The results could decide whether the universe's geometry itself obeys the rules of the quantum. Even the most speculative ideas are finding experimental expression. The holographic principle, once a purely mathematical insight, might leave detectable traces in the noise of spacetime. The holometer experiment at Fermilab sought to measure correlations in quantum fluctuations of position, a kind of space-time jitter that would indicate the holographic discreteness of reality. Though no signal has yet been found, the search continues, each null result refining our understanding of what space-time is and what it is not. Across the world, technology is converging toward a new kind of physics, one where gravity is tested, not by celestial orbits, but by laboratory precision. Quantum sensors, atomic clocks, and superconducting resonators now measure time and distance with accuracies that brush against the Planck scale. Every improvement brings us closer to seeing the grain of space-time, to detecting how quantum information weaves the geometry we live in. It is a revolution, not of size but of sensitivity, transforming the tabletop laboratory into a microscope for the fabric of the universe. Even as we reach for these tiny experiments, the cosmos itself performs the grandest ones for us. In the centers of galaxies, black holes merge and evaporate, encoding and releasing information in ways we barely understand. The cosmic web, stretched by dark energy, may be the visible trace of spacetime's entanglement evolving through eons. Observing these vast systems gives us data that no human could ever reproduce on Earth. In every photon from a distant quasar, in every ripple of gravitational waves, there lies the potential to decode the quantum geometry of existence. Perhaps the ultimate experiment is the universe itself, its expansion, its structure, its background radiation. All these are the outputs of an ongoing computation written in the laws of quantum gravity. Each observation we make refines our model of that computation, narrowing the gap between theory and reality. The boundary between the classical and the quantum grows thinner with every measurement, revealing that the difference may not be fundamental at all, but merely a matter of scale. The quantum and the cosmic are not two realms, but two faces of the same whole. In the coming decades, as technology continues to evolve, we may finally test whether gravity can carry entanglement, whether space-time vibrates with quantum discreteness, and whether information truly weaves the universe. The day we confirm that gravity is quantum will not be just another scientific milestone. It will mark the completion of a story that began with Newton's falling apple and continued through Einstein's curved space-time. It will mean that every force in nature speaks the same language, and that the geometry of the universe is nothing less than the expression of its quantum heart. And yet, if those experiments were to show that gravity resists quantization, the result would be no less profound. It would mean that space-time is not merely quantum, but emergent from something deeper still, perhaps from pure information, or from principles we have not yet imagined. Either outcome will reshape our understanding of what reality is. The question is no longer whether we can probe quantum gravity, but how soon we will see its signature. The horizon of discovery is no longer infinite. It is approaching, bright with possibility. When that moment comes, when the first undeniable evidence of gravity's quantum nature is seen, the universe will become newly transparent. We will have glimpsed the code beneath its surface, the logic that ties the motion of galaxies to the trembling of atoms. We will understand that the cosmos is not merely governed by mathematics. It is mathematics, written in the language of information and realized through the geometry of space-time. Gravity, the oldest mystery, will have revealed its final secret, that it, too, is part of the great quantum conversation that sustains reality. Reality has always seemed solid. The floor beneath our feet, the stars above, the ticking of clocks, all appear grounded in certainty. But beneath that surface, the universe is anything but stable. It trembles with quantum fluctuations, whispers with probabilities, and hums with entanglement. Gravity, once thought to be the most classical of forces, now seems to belong to this same uncertain world. The evidence gathered from black holes, entanglement, and the holographic universe suggests that space-time itself is a quantum system, and that everything we experience may arise from its information structure. Einstein described gravity as geometry, the curvature of space-time caused by mass and energy. Quantum mechanics, on the other hand, describes a world of uncertainty and superposition. For nearly a century, these two visions have stood apart. Yet as the evidence has grown, a new understanding has begun to take shape. The smooth geometry of Einstein and the probabilistic dance of quantum theory are not rivals but partners, two perspectives on a single reality. The key that binds them is information. Information, in this context, is not something human or symbolic. It is the fundamental bookkeeping of the universe, the record of every possible state, every interaction, every quantum correlation. When information is arranged in particular ways, it produces the emergent phenomena we call matter, energy, and space-time. Gravity, rather than being a basic force, is the large-scale behavior of that informational geometry-seeking balance. It is entropy made visible, the curvature of knowledge itself. This realization changes how we see everything. A planet orbiting a star is not being pulled by an invisible force. It is following the path of least informational resistance, the route that keeps the network of space-time coherent. The expansion of the universe is not a pushing outward of galaxies, but a reconfiguration of quantum information, spreading entanglement across cosmic scales. Even the passage of time, our most familiar illusion, may be nothing more than the continual rewriting of information, the flow of entropy through the quantum web of existence. If the universe is an information processor, then the laws of physics are its operating rules. Quantum mechanics describes how information changes on small scales. General relativity describes how the large-scale geometry responds to those changes. Together, they form a cosmic computation, a vast, self-consistent algorithm running on the hardware of space-time. Every particle interaction, every flash of light, every heartbeat is a line of code executing in that great program. Reality is not made of things but of relationships, of bits woven into form through the grammar of the quantum. The holographic principle reinforces this vision. It tells us that everything occurring in a volume of space can be described by data stored on its boundary. What we experience as three-dimensional space is a projection of two-dimensional information. The universe is, in this sense, a cosmic hologram, not an illusion, but an emergent image produced by the interplay of quantum bits. When gravity bends light, when stars collapse into black holes, when galaxies swirl in dark matter halos. They are all manifestations of how information arranges itself across those boundaries. The geometry we inhabit is the visible texture of invisible computation. At the smallest scales, space-time becomes granular, a froth of quantum foam where distance, time, and causality lose their familiar meaning. Yet, from that microscopic chaos, order emerges. The average of all those fluctuations smooths into the continuum of general relativity, much as countless molecules create the illusion of a calm sea. The macroscopic world, stable and predictable, is the collective behavior of innumerable quantum processes, obeying the simple rule that information must be conserved. The universe keeps perfect accounts. Nothing is ever truly lost, not even in the heart of a black hole. This unity between information and geometry leads to profound questions. If everything we observe is emergent, what is the substrate from which it emerges? Is there a realm more fundamental than space-time, a pre-geometric reality from which even quantum mechanics arises? Some physicists suspect that the answer lies in pure mathematics, in structures that exist outside time, describing relations without objects. Others imagine a pre-space-time network of quantum bits, a primordial computation whose patterns give birth to causality and existence. In such a model, the universe did not begin with the Big Bang as an explosion in space, but as the ignition of information itself, the moment when order began to unfold from possibility. Perhaps, too, consciousness plays a role in this unfolding. If information is the basis of reality, and if consciousness is what experiences and processes information, then the two may be reflections of the same principle viewed from different sides. The observer and the observed would not be separate. They would be entangled, each defining the other. In this way, the act of observation becomes not a disturbance of reality, but its continuation, the means by which the universe knows itself. Yet even without invoking mind, the informational view of physics reshapes our deepest intuitions. It tells us that energy is the capacity to transform information, that entropy measures the number of ways information can be arranged, and that gravity is the statistical consequence of these transformations. The universe evolves because information seeks equilibrium, just as heat flows from hot to cold. The arrow of time, the growth of structure, the emergence of galaxies and life, all are expressions of this single principle. In the coming decades, as experiments probe gravity at the quantum level, we may finally confirm this vision. The interference of tiny masses, the entanglement mediated by gravitational fields, the subtle quantum fluctuations in gravitational waves, all could reveal that space-time itself obeys quantum rules. If they do, we will have proved that the universe is consistent all the way down, that the same laws govern both atoms and galaxies, and that geometry itself is a quantum entity. But even if gravity resists quantization, even if it turns out to be emergent from information rather than fundamental, the conclusion is no less astonishing. It would mean that reality is not built from forces and particles, but from meaning, from relationships encoded in the structure of existence. The universe would be not a mechanism, but a message, unfolding across time through the logic of information. In either case, we will have arrived at the same truth, that the boundary between physics and philosophy, between matter and thought, is an illusion. The cosmos is not separate from our understanding of it. The equations we write are not descriptions of an external world, but expressions of the same logic that gives rise to that world. To study gravity, to quantize it, is to study the language in which reality speaks itself into being. And so, the oldest question in science, what is gravity, becomes inseparable from the oldest question in philosophy, what is reality? The answer, whispered through equations and black holes and entangled particles, may be this: reality is not made of matter, nor of energy, but of information. The universe is a self-writing code, its structure woven from the quantum threads of connection. Gravity is its geometry, space-time its syntax, and consciousness its reading of the text. If gravity is indeed a quantum effect, then everything we know, from the flicker of starlight to the flow of time, is the unfolding of a single cosmic computation. The universe is not a stage upon which existence plays out. It is the play itself, the story being written as it is told. Each of us, every atom and every galaxy, is a line in that story, a piece of the code through which reality knows its own existence. Perhaps in the end, that is what gravity truly is: the quiet pull of information toward coherence, the tendency of the universe to remain whole. It is the most fundamental connection, the one that binds space to time, matter to energy, and thought to being. The force that will not fit into our equations is not a force at all, but the harmony of everything that exists. If gravity is a quantum effect, then reality itself is built not from matter or energy, but from information, weaving the universe from entangled threads of light and time.